There are moments in human history when everything changes. When a discovery is so profound that it shifts the way we see ourselves, our world, and our place among the stars. We stand at the threshold of one such moment. Hello, and welcome to Infinite Science. What you're about to hear may be the most significant discovery in the history of our species. For the first time, we may have found evidence of life beyond Earth. Not a possibility, not a probability, but tangible, measurable signs that somewhere out there beneath alien skies and around a distant sun, life exists. This isn't science fiction. This is science fact unfolding in real time, powered by the most sophisticated instruments humanity has ever built. And the world we've found, it might be even better than our own. Take a breath, let that sink in. We are no longer alone in asking whether life exists beyond Earth. We may now be asking, what is that life like? For centuries, we've gazed up at the night sky and wondered. Philosophers pondered. Scientists theorized. Dreamers imagined. But wonder, no matter how profound, cannot answer the question that has haunted us since we first looked up. Are we alone? Now, for the first time, we may have our answer. This is a story about discovery, about human curiosity, about a planet 120 light years away that could rewrite everything we thought we knew about life in the universe. And it's a story that begins not with telescopes or data, but with a simple, timeless question. Are we the only ones? The answer, whispered across the void in wavelengths of infrared light, analyzed by instruments of almost incomprehensible precision, may finally be within our grasp. And if that answer is what the evidence suggests, if life truly exists on this distant world, then we stand at the beginning of a new chapter in human understanding. Every civilization has its defining moments: the mastery of fire, the invention of writing, the Industrial Revolution, the splitting of the atom, the decoding of DNA, the first steps on the moon. Each of these moments expanded the boundaries of what we thought possible, transformed our relationship with the world, and opened new frontiers of knowledge and capability. The discovery of life beyond Earth would eclipse them all, because this isn't just about finding microbes on a distant planet. It's about understanding our place in a universe that may be teeming with life. It's about recognizing that the processes that led to us, the chemistry and evolution, and the long march from simple molecules to complex organisms, are not unique accidents, but natural consequences of the laws of physics operating across cosmic time. We are about to explore a world that challenges everything we thought we knew about the limits of habitability. A world where the conditions for life might be not just adequate, but superior to our own. A world that forces us to reimagine what's possible. So settle in. Turn off the distractions. Open your mind to wonder. Because what you're about to discover will change the way you see the night sky, the way you think about Earth, and the way you understand your place in the cosmos. This is the story of K2-18b, a world in the constellation Leo, a planet that might host life. A discovery that may represent the most important scientific finding in human history. Let's begin. The search for life beyond Earth is woven into the fabric of human consciousness. It's one of the oldest questions we've ever asked, transcending cultures, eras, and belief systems. Ancient civilizations looked to the heavens and saw gods, omens, and infinite mystery. But it wasn't until we understood that those distant lights were actually other worlds that the question transformed from mythology to science. The ancient Greeks debated whether the cosmos contained other inhabited worlds. Epicurus, in the 3rd century BCE, argued that infinite worlds must exist in the infinite universe. Lucretius expanded on this, suggesting that nature's laws must operate uniformly throughout the cosmos, making life elsewhere not just possible but probable. These were philosophical arguments, beautiful in their logic but untestable with the tools available. For centuries, the question remained in the realm of speculation. Copernicus moved Earth from the center of the universe, making us one planet among others orbiting the Sun. Galileo turned his telescope to Jupiter and saw moons orbiting that distant world, proving that not everything in the heavens revolved around Earth. The Copernican principle emerged. Earth is not special. We occupy no privileged position in the cosmos. If Earth isn't special, then perhaps life isn't unique to Earth. In the 1800s, astronomers observed what they thought were canals on Mars, straight lines suggesting intelligent construction. Percival Lowell championed the idea of Martian civilization, proposing that an advanced society had built an irrigation network to transport water from the polar ice caps to the equatorial deserts. The canals turned out to be optical illusions, but the idea captured public imagination. For the first time, extraterrestrial life wasn't just philosophical speculation. It was something people genuinely believed existed in our own solar system. The 20th century brought both hope and disappointment. The space age began with Sputnik in 1957, followed by Yuri Gagarin's orbital flight and Neil Armstrong's steps on the Moon. We sent probes to Mars expecting to find life. Viking 1 and Viking 2 landed on the Martian surface in 1976, equipped with experiments specifically designed to detect biological activity. The results were ambiguous, tantalizing, ultimately inconclusive. Mars, as far as we could tell, was sterile. But Mars wasn't the only option. In the 1960s and 70s, scientists began seriously considering the possibility of life on other planets beyond our solar system. The problem was simple. We didn't know if other planets existed. Stars are bright, planets are dim, tiny dots lost in their star's glare. Detecting a planet orbiting another star would be like spotting a firefly next to a lighthouse from 1,000 miles away. It seemed nearly impossible, yet astronomers persisted. They developed techniques to detect planets indirectly. The radial velocity method measures the tiny wobble a planet causes in its star's motion as gravity pulls them around their common center of mass. The transit method detects the minuscule dimming of starlight when a planet passes in front of its star from our perspective. And then, in 1995, everything changed. Astronomers Michel Mayor and Didier Queloz, working at the Observatoire de Haute-Provence in France, announced the discovery of 51 Pegasi b, the first confirmed exoplanet orbiting a Sun-like star. It was nothing like Earth. A gas giant, roughly half the mass of Jupiter, orbiting impossibly close to its star with a year lasting just over 4 days. The surface temperature was estimated at over 1,800 degrees. No chance of life as we know it, but it proved something revolutionary. Other worlds exist. The floodgates opened. Within a year, several more exoplanets were discovered. Within a decade, dozens. Astronomers realized that planets weren't rare cosmic accidents. They were common, perhaps even universal around stars. Every technique improved. Every telescope contributed. The catalogue of known exoplanets grew exponentially. But quantity wasn't enough. We needed quality. We needed to find planets that could potentially host life, rocky worlds in their star's habitable zone, with conditions that might allow liquid water to exist on their surfaces. NASA launched the Kepler Space Telescope in 2009 with a singular mission: stare at a single patch of sky containing about 150,000 stars and measure their brightness continuously, watching for the telltale dimming that indicated a planetary transit. Kepler was phenomenally successful. Over its 9-year mission, it discovered over 2,600 confirmed exoplanets and identified thousands more candidates awaiting verification. The statistical picture that emerged was stunning. Kepler's data suggested that virtually every star in our galaxy hosts at least one planet. Some have multiple planets, entire solar systems of worlds orbiting in complex gravitational dances. The Milky Way contains at least 100 billion stars. That means hundreds of billions of planets, perhaps trillions. And among those countless worlds, Kepler found thousands of rocky planets roughly Earth size. Many orbit in their star's habitable zone, the region where temperatures could allow liquid water. These planets became known as Earth analogues or Earth candidates, worlds that might, just might, be similar enough to our own to support life. But discovering a potentially habitable planet and confirming that it actually hosts life are vastly different challenges. Distance is the ultimate barrier. Even the nearest stars are light years away. Alpha Centauri, our closest stellar neighbor, is 4.37 light-years distant. That's about 25 trillion miles. Traveling at the speed of our fastest spacecraft, Voyager 1, it would take over 70,000 years to reach. We can't visit these worlds. We can barely see them. Most exoplanets have never been directly imaged. We know they exist only through indirect measurements. The wobble of their star, the dimming of starlight during a transit, the gravitational lensing of background objects. To search for life, we need to study exoplanet atmospheres. We need to detect the chemicals present in the air of these distant worlds and look for biosignatures, molecules that indicate biological processes. On Earth, oxygen makes up 21% of our atmosphere. It's so reactive that it would quickly disappear, combining with other elements unless something constantly replenished it. That something is life. Photosynthetic organisms, from microscopic phytoplankton to massive rainforests, producing oxygen as they convert carbon dioxide and water into energy. Methane is another potential biosignature. On Earth, microbes produce vast quantities of methane. So do geological processes, but in smaller amounts. Finding methane and oxygen together would be particularly compelling because they react with each other and wouldn't coexist without constant replenishment. The Hubble Space Telescope, launched in 1990, contributed to exoplanet science by analyzing the atmospheres of some hot Jupiters, gas giants orbiting close to their stars. Hubble detected water vapor, sodium, and other molecules. But Hubble had limitations. It was designed primarily for visible and ultraviolet light. Many of the most revealing atmospheric signatures exist in the infrared spectrum, wavelengths Hubble couldn't access with sufficient sensitivity. To truly study exoplanet atmospheres, to search for biosignatures with the precision needed to make confident detections, we needed something more powerful. Something specifically designed to peer into the infrared, to analyze the chemical composition of distant worlds with unprecedented accuracy. We needed an observatory that could look deeper into space and time than anything before it. An instrument so sensitive it could detect the heat signature of a bumblebee on the moon. A telescope with a mirror so large and precisely engineered that it could resolve details impossible for any previous observatory. We needed to build something that had never been built before. Something that would push the boundaries of human engineering and scientific ambition to their absolute limits. We needed the James Webb Space Telescope. And on December 25, 2021, after 3 decades of development, countless challenges, and moments when the entire project seemed doomed to failure, we launched it. the search for life beyond Earth had entered a new era. An era where we would no longer simply wonder, an era where we would search with instruments capable of finding answers. And those answers were waiting, encoded in starlight, crossing the void, carrying secrets from worlds we had barely begun to imagine. Life, as we understand it, is fragile. It requires precise conditions, a delicate balance of factors that must align like tumblers in a cosmic lock. Get one wrong, and a world becomes a frozen wasteland or a scorched hellscape. Understanding what makes a planet habitable is fundamental to our search for life beyond Earth. Let's start with the most famous requirement, the habitable zone, often called the Goldilocks zone. Not too hot, not too cold, just right. A planet must orbit its star at the perfect distance where temperatures allow liquid water to exist on its surface. This distance varies depending on the star's temperature and luminosity. Our Sun is a G-type yellow dwarf, relatively stable and medium-sized. Earth orbits at about 93 million miles, receiving just enough energy to maintain an average surface temperature, around 59 degrees. Move us significantly closer, and we become Venus, where a runaway greenhouse effect has created surface temperatures hot enough to melt lead. Move us farther out, and we become Mars, where thin atmosphere and distance from the Sun have left the surface frozen and barren. But the habitable zone isn't a simple ring at a fixed distance. It's a complex region that depends on multiple factors. A planet's atmosphere plays a crucial role. Greenhouse gases like carbon dioxide and water vapor trap heat, allowing a planet to remain warm enough for liquid water even if it orbits somewhat farther from its star. Without an atmosphere, even a planet in the habitable zone would freeze. Venus demonstrates the dangers of too much greenhouse effect. Its atmosphere is 96% carbon dioxide, creating a crushing surface pressure 90 times that of Earth and temperatures around 900 degrees. Venus orbits closer to the Sun than Earth, but its extreme conditions are less about distance and more about atmospheric composition. The thick blanket of CO2 traps heat so efficiently that Venus is actually hotter than Mercury, despite Mercury being closer to the Sun. Mars shows the opposite problem. It once had a thicker atmosphere, liquid water flowing across its surface, perhaps even oceans. But Mars is small, with weak gravity, and it lost its magnetic field early in its history. Without magnetic protection, solar wind gradually stripped away the Martian atmosphere. Today, the atmospheric pressure on Mars is less than 1% of Earth's. Any liquid water on the surface would immediately boil away into space or freeze solid, depending on temperature. Mars is technically in the Sun's habitable zone, but it lost the atmospheric conditions needed to remain habitable. This brings us to another critical factor: magnetic fields. Earth's magnetic field is generated by the movement of molten iron in our planet's outer core. This creates a protective bubble called the magnetosphere that extends thousands of miles into space. When charged particles from the Sun, carried by the solar wind, encounter the magnetosphere, they're deflected around Earth. Some particles get funneled toward the magnetic poles, where they collide with atmospheric molecules and create the aurora borealis and aurora australis, the beautiful northern and southern lights. Without this magnetic shield, solar wind would gradually strip away Earth's atmosphere, just as it did on Mars. Our magnetic field is one of the unsung heroes of habitability, an invisible force field protecting the delicate balance of gases that makes life possible. Water is the universal solvent, the medium in which life's chemistry unfolds. Every organism on Earth requires water. It's not just that we need it to drink. Water is fundamental to biochemistry. It dissolves nutrients, transports molecules, facilitates reactions, and regulates temperature. We don't know if life can exist without water because we've never encountered life that doesn't depend on it. Absolutely. A habitable planet needs not just water vapor in its atmosphere, but liquid water in abundance. Oceans, lakes, rivers, rain, water cycling through different states, evaporating from surfaces, forming clouds, falling as precipitation, flowing back to reservoirs. This hydrological cycle distributes heat, moderates temperature extremes, and creates diverse environments where life can adapt and thrive. Earth's water content is perfect. Too little, and we'd be a desert world with limited environments for life. Too much, and we'd be an ocean world with no land masses. Earth has both. Vast oceans covering 71% of the surface and continents providing diverse terrestrial environments. This combination has been crucial to the evolution of complex life. Marine organisms evolved first, but the colonization of land opened entirely new ecological niches, driving evolution in directions that wouldn't have been possible in an ocean-only world. Atmospheric composition matters immensely. Earth's atmosphere is 78% nitrogen, 21% oxygen, and trace amounts of argon, carbon dioxide, and other gases. This composition isn't arbitrary. Nitrogen is relatively inert, providing atmospheric bulk without reacting with other elements. Oxygen is highly reactive, essential for complex metabolism, but also potentially dangerous. Plants and photosynthetic bacteria produce oxygen while animals and other organisms consume it. The balance is maintained by the biosphere itself, but oxygen wasn't always abundant on Earth. For the first 2 billion years of Earth's history, the atmosphere contained almost no free oxygen. It was only after photosynthetic cyanobacteria evolved and began pumping oxygen into the atmosphere that levels rose. This great oxidation event, about 2.4 billion years ago, was initially catastrophic for anaerobic organisms that couldn't tolerate oxygen. But it paved the way for complex life, providing the energy-rich metabolism needed for large, active organisms. The lesson: a habitable planet's atmosphere can change dramatically over time, shaped by geological processes and life itself. Stability is crucial. A planet's orbit should be relatively circular, avoiding wild temperature swings between closest and farthest approach to the star. Earth's orbit is nearly circular, with an eccentricity of only 0.01. Some exoplanets have highly elliptical orbits, swinging from scorching heat to frozen cold over the course of a single year. Such extreme variations would make it difficult for life to establish and persist. A planet's rotation matters too. Earth rotates once every 24 hours, providing regular day-night cycles that allow one side to warm while the other cools. If Earth were tidally locked, with one side permanently facing the sun and the other in eternal darkness, conditions would be far more extreme. The day side might be too hot, the night side too cold, with only a narrow twilight zone potentially habitable. Some exoplanets, particularly those orbiting close to small, cool stars, are likely tidally locked. Scientists debate whether such worlds could still be habitable. Perhaps a thick atmosphere could redistribute heat from the day side to the night side. Perhaps life could adapt to the permanent conditions on either side. We simply don't know yet. The host star itself is a critical factor. Stars come in many varieties, from massive, short-lived blue giants to tiny, long-lived red dwarfs. Our Sun is a G-type star, stable and middle-aged at about 4.6 billion years old. It will continue shining for another 5 billion years before swelling into a red giant and eventually dying. Smaller stars, K-type orange dwarfs and M-type red dwarfs, are particularly interesting for habitability. They're cooler than the Sun, so their habitable zones are closer in, but they're also far more numerous and longer-lived. A red dwarf can shine for tens or even hundreds of billions of years, providing a stable environment for life to evolve over timescales that dwarf Earth's history. However, small stars have a problem. They're often active when young, producing intense flares and high-energy radiation that could sterilize nearby planets. A planet in the habitable zone of a red dwarf would need a strong magnetic field and thick atmosphere to survive the star's violent youth. Time is perhaps the most underappreciated factor in habitability. Life on Earth took hundreds of millions of years to emerge after conditions became suitable. Simple, single-celled organisms dominated for billions of years before complex multicellular life evolved. Intelligence and technology emerged only in the last few million years, a blink of an eye in geological time. A habitable planet needs to remain habitable long enough for life to take root, survive periodic catastrophes like asteroid impacts and volcanic eruptions, and gradually evolve in complexity. Earth's 4.5 billion-year history has been tumultuous, with multiple mass extinctions, but life has persisted, adapted, and diversified. Earth checks every box on the habitability checklist. We orbit a stable, medium-sized star at the perfect distance. We have abundant liquid water covering most of our surface. Our atmosphere is rich with oxygen, maintained by billions of years of photosynthetic life. Our magnetic field protects us from solar wind. Our moon stabilizes our axial tilt, preventing extreme climate shifts that would occur if Earth wobbled chaotically. Our position in the Milky Way is relatively calm, away from the violent stellar nurseries and supernova-prone regions near the galactic core. We are, by all measures, extraordinarily lucky. But here's the profound realization that's emerged from decades of exoplanet research. Earth-like conditions might not be as rare as we once thought. The galaxy is vast. With hundreds of billions of stars and potentially trillions of planets, even long odds become near certainties when you play the game enough times. Statistical analysis of Kepler data suggest that roughly 20–50% of Sun-like stars have rocky planets in their habitable zones. That's tens of billions of potentially habitable worlds in our galaxy alone. Not all will have the right atmospheric composition. Not all will have magnetic fields. Not all will remain stable long enough for life to evolve. But even if only a tiny fraction meet all the requirements, we're still talking about millions or billions of habitable planets. The question isn't whether habitable worlds exist. We know they do. The question is whether we can find them, study them, and detect the unmistakable signs of life. For that, we needed to build something unprecedented, an observatory that could peer across light years of space and analyze the atmospheres of distant worlds with exquisite precision. An instrument that could detect molecules in alien air and determine whether those molecules were produced by geological processes or by life itself. We needed the James Webb Space Telescope, and when it finally launched, after decades of development and anticipation, it exceeded our wildest expectations. On December 25, 2021, a European Ariane 5 rocket lifted off from the Guiana Space Center in Kourou, French Guiana. Watching from around the world were thousands of scientists, engineers, and space enthusiasts, many of whom had devoted decades of their careers to this moment. Inside the rocket's protective fairing, folded like an intricate piece of cosmic origami, was humanity's most ambitious scientific instrument, the James Webb Space Telescope. The journey to this launch had been long and fraught with challenges. Planning for Webb began in the 1990s, shortly after the Hubble Space Telescope's launch. Hubble had revolutionized astronomy, but scientists already understood its limitations. Hubble operated primarily in visible and ultraviolet light, to peer deeper into the universe's past, to study the formation of the first galaxies, to analyze the atmospheres. Of exoplanets, we needed an observatory that could see in infrared. Infrared radiation is heat. Everything in the universe emits it: stars, planets, dust clouds, even you. Warmer objects emit more infrared radiation at shorter wavelengths, while cooler objects emit at longer wavelengths. But infrared has another crucial property. The expansion of the universe stretches light from distant objects toward longer, redder wavelengths. The most distant galaxies, formed just hundreds of millions of years after the Big Bang, have had their visible light redshifted into the infrared spectrum. To see them, we need infrared eyes. Infrared observation presents unique challenges. Earth's atmosphere absorbs most infrared wavelengths, which is why ground-based infrared telescopes are built at high, dry locations like mountaintops in Chile or Hawaii. But even the best ground-based sites can't overcome all atmospheric interference. Space-based observation is essential. More challenging still, the INUM telescope itself emits infrared radiation because it has temperature. If Webb's instruments operated at room temperature, their own heat would overwhelm the faint signals from distant objects. It would be like trying to photograph distant candles while sitting next to a bonfire. The solution? Keep Webb incredibly cold. The instruments operate at about 320 degrees, just 50 degrees above absolute zero. To achieve this, Webb was sent to a location far from Earth's heat and equipped with a massive sunshield. 29 days after launch, Webb arrived at Lagrange Point 2, or L2, a gravitationally stable position about 1 million miles from Earth in the direction away from the Sun. At L2, the gravitational pulls of the Earth and Sun balance perfectly, allowing Webb to maintain its position with minimal fuel consumption. It's like a cosmic parking spot where gravity does most of the work. But getting to L2 was just the beginning. Now came the most nerve-wracking phase: deployment. Webb had been folded to fit inside the rocket fairing, which was only 18 feet in diameter. The telescope itself is enormous: a primary mirror 21 feet across and a sunshield the size of a tennis court. Over 2 weeks, Webb began the delicate process of unfolding, each step choreographed and tested thousands of times on Earth, but now happening 1 million miles away where no repair mission would be possible. The sunshield deployed first. 5 layers of Kapton film, each thinner than a human hair, stretched out like a massive kite. Each layer is separated from the next by gaps that allow heat to radiate away into space. The sunshield's job is to block heat and light from the Sun, Earth, and Moon, all of which would warm the instruments and ruin their sensitivity. The temperature difference across the sunshield is staggering. The sun-facing side heats up to about 230 degrees, while the shadowed side, where the instruments sit, drops to 370 degrees Celsius. This 600-degree temperature gradient is maintained by the 5-layer design, with each layer reflecting and radiating heat away. Next came the mirror. Webb's primary mirror is composed of 18 hexagonal segments, each made of beryllium and coated with a microscopically thin layer of gold. Gold reflects infrared light exceptionally well, making it perfect for Webb's mission. Each segment is 4.3 feet across and weighs about 88 pounds. Together, they form a mirror with a collecting area of about 270 square feet, nearly 6 times larger than Hubble's. But the mirror wasn't deployed as a single piece. Each segment unfolded and locked into place, then required precise alignment. Using actuators controlled from Earth, Engineers adjusted each segment's position and curvature to nanometer precision, aligning them to function as a single, perfect mirror. This process took months of painstaking work. By July 2022, 6 months after launch, Webb was fully deployed, aligned, and calibrated. The first images were released to the public, and they were breathtaking. Galaxies from the early universe, never before seen. Star-forming nebulae revealed in unprecedented detail. Exoplanet atmospheres analyzed with precision that made Hubble's observations look primitive by comparison. Webb doesn't see visible light the way Hubble does. It sees infrared, which means its images are initially invisible to human eyes. The data is translated into colors we can perceive, with shorter infrared wavelengths mapped to blue and longer wavelengths to red. The result is images that look alien and beautiful, revealing structures hidden from visible light telescopes. So how does Webb study exoplanets? The technique is called transmission spectroscopy, and it's remarkably elegant. When a planet passes in front of its star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths of light. Oxygen absorbs certain wavelengths. Water, vapor, absorbs others. Methane, carbon dioxide, ammonia, each leaves its unique signature, like a molecular barcode. Webb's instruments spread this filtered starlight into a spectrum, a rainbow of wavelengths. By measuring which wavelengths are dimmer than expected, scientists can identify which molecules are present in the atmosphere. It's chemistry from across the galaxy. Webb has 4 main instruments, each a marvel of engineering. NIRCam captures stunning images in the near-infrared spectrum. It's Webb's primary imager, responsible for most of the beautiful photos released to the public. NIRCam also serves as Webb's wavefront sensor, analyzing the alignment of the mirror segments. NIRSpec analyzes chemical compositions by spreading light into spectra. It can observe up to 100 objects simultaneously using a microshutter array, making it incredibly efficient for studying multiple stars or galaxies at once. MIRI observes cooler objects and dust in the mid-infrared range. It requires even colder temperatures than the other instruments, so MIRI has its own dedicated cooling system that brings it down to 147 degrees Celsius, just a few degrees above absolute zero. NIRIS specializes in exoplanet atmospheres and faint object detection. It's particularly good at transmission spectroscopy, making it a key instrument for searching for biosignatures. Together, these instruments make Webb the most powerful observatory in human history. It can see farther, deeper, and more clearly than anything before it. It can study the formation of stars in dusty nebulae that block visible light. It can probe the atmospheres of planets around other stars. It can look back to the cosmic dawn, observing galaxies that formed just a few 100 million years after the Big Bang. Webb's sensitivity is almost incomprehensible. It could detect the heat signature of a bumblebee at the distance of the Moon. It can observe objects 100 times fainter than what Hubble could see. Its spectrographs can identify individual molecules in exoplanet atmospheres from hundreds of light years away. This is the instrument we've built to search for life. This is the culmination of decades of dreaming, planning, engineering, and persistence. This is humanity's eye on the cosmos, opened wider than ever before. And when Webb turned its gaze toward a small, unremarkable star 120 light-years away in the constellation Leo, it found something extraordinary, something that might change everything. The constellation Leo has been recognized for millennia. Ancient Egyptians saw it as sacred, associating it with the annual flooding of the Nile that brought fertility to their lands. Greek mythology placed it in the heavens as the Nemean lion, a creature with impenetrable skin slain by Heracles as the first of his 12 labors. Roman astronomers, Chinese sky watchers, Arabic scholars all recognized Leo's distinctive pattern, the lion's mane and body arcing across the spring sky. For most of human history, the stars of Leo were just that, stars. Distant lights in fixed patterns, beautiful and eternal. We knew nothing of their true nature. We didn't know they were suns like our own. We certainly didn't know that around those suns orbited worlds. But we know now. Oh, how we know. 120 light-years from Earth in the direction of Leo's hindquarters, there is a star. Its designation is unremarkable. K2-18. To the naked eye, it's completely invisible, far too faint to see without a telescope. You could stare at that patch of sky your entire life and never know it was there. Even through a small amateur telescope, it's just one anonymous point of light among millions. K2-18 is what astronomers call a K-type orange dwarf, a star smaller and cooler than our Sun. If you could stand on a planet orbiting K2-18, the sky would look different than it does on Earth. The star would appear orange-red rather than yellow-white, casting the world in a warm, almost firelight glow. The star's diameter is about 45% of our Sun's, and it produces only about 3% of the Sun's total energy output. But K-type stars have advantages. They're incredibly common, making up about 13% of all stars in the galaxy. More importantly, they're stable and long-lived. Our Sun will shine for about 10 billion years total. K-type stars can shine for 20, 30, even 50 billion years. They provide stable environments for planetary systems over timescales that dwarf the entire history of Earth. Around K2-18, something remarkable orbits. The planet was first detected by NASA's Kepler Space Telescope during its extended K2 mission in 2015. The detection method was simple in concept. Kepler stared at K2-18 continuously, measuring its brightness. Every 33 days, like clockwork, the star's light dimmed slightly, dropping by about 0.1%. That minuscule dimming indicated something passing in front of the star from our perspective. A transit, a planet. Follow-up observations confirmed it. The planet, designated K2-18b, is real. It orbits its star every 33 days at a distance of about 16 million miles, much closer than Earth's 93 million-mile orbit around the Sun. But remember, K2-18 is cooler than our Sun. At that closer distance, the planet receives a similar amount of energy as Earth does, placing it squarely in the habitable zone. The planet's size was estimated from the depth of the transit. The more of the star's light gets blocked, the larger the planet. K2-18b is about 2.6 times Earth's radius. Follow-up observations using the radial velocity method, measuring the tiny wobble K2-18b causes in its star's motion, allowed scientists to estimate its mass, roughly 8 to 9 times Earth's mass. This makes K2-18b a super-Earth, a class of planet we don't have in our solar system. Super-Earths are larger than Earth but smaller than Neptune. They're incredibly common in the galaxy, perhaps the most common type of planet. Yet we don't have one locally to study, which makes them both fascinating and mysterious. Super-Earths occupy a middle ground. Are they rocky worlds like Earth, just bigger? Or are they more like mini-Neptunes, with thick hydrogen and helium atmospheres surrounding small, rocky cores? K2-18b's mass and radius suggested something in between. It was too dense to be a mini-Neptune, but too large to be purely rocky. Scientists proposed it might be a water world, a planet with a deep global ocean, perhaps hundreds of miles deep, sitting atop a rocky core. But ocean or rock, size and mass and orbital distance, These were just numbers. They told us about K2-18b's physical properties, but nothing about whether it was actually habitable, whether it had the conditions needed for life. For that, we needed to study its atmosphere. In 2019, astronomers used the Hubble Space Telescope to observe K2-18b during several transits. As starlight filtered through the planet's atmosphere, Hubble's spectrograph analyzed which wavelengths were absorbed. The results made headlines. Water vapor. Hubble had detected water vapor in K2-18b's atmosphere. This was significant. K2-18b was the first potentially habitable exoplanet, meaning rocky, and in the habitable zone where water vapor had been confirmed. But water vapor alone doesn't mean much. Venus has water vapor. Jupiter has water vapor. What mattered was the context. Was there liquid water on the surface? What else was in the atmosphere? What were the temperature and pressure conditions? Hubble's data was limited. The observations were at the edge of the telescope's capabilities, and the uncertainties were large. Scientists knew there was water vapor, but they couldn't characterize the atmosphere in detail. They couldn't search for biosignatures, the molecules that would indicate the presence of life. Those questions required better data. They required more sensitivity, better spectral resolution, access to wavelengths Hubble couldn't observe. They required the James Webb Space Telescope. In 2023, Webb turned its golden eye toward K2-18b. The observations were planned meticulously. Webb would observe the star during multiple transits, capturing the filtered starlight with its NIRISS instrument. Each transit lasted several hours as the planet crossed in front of its star. The data would be combined from multiple transits to improve the signal-to-noise ratio, allowing scientists to detect even trace amounts of atmospheric molecules. The data came back, transmitted across 1 million miles from Webb's orbit at L2 to receiving stations on Earth. Teams of scientists around the world, coordinated through the international collaboration that operates Webb, began the painstaking work of analysis. Raw data had to be calibrated, corrected for instrumental effects, and processed through sophisticated algorithms that could extract the planetary atmosphere's spectral signature from the star's overwhelming brightness. Weeks passed, then months. Scientific analysis doesn't happen overnight. Every step must be verified, every result checked and rechecked. Alternative explanations must be considered and ruled out. Uncertainties must be quantified. Only then can results be announced with confidence. And what they found changed everything. The atmosphere of K2-18b contains water vapor, as Hubble had shown. But Webb's superior sensitivity revealed far more. Carbon dioxide was present in significant quantities. This was expected. CO2 is common in planetary atmospheres. But then there was methane, lots of it. Methane, CH4, is a simple molecule. One carbon atom bonded to 4 hydrogen atoms. On lifeless planets, methane doesn't last long. Ultraviolet light from the star breaks it down. It reacts with other atmospheric chemicals. Without constant replenishment, methane disappears from an atmosphere in thousands or millions of years, a blink of an eye in planetary timescales. On Earth, the vast majority of atmospheric methane comes from biological sources. Wetlands account for about 1/3 of global methane emissions. Microbes in swamps, bogs, and rice paddies produce methane as they digest organic matter in oxygen-free environments. Ruminant animals like cows, sheep, and goats produce methane in their digestive systems. Termites produce methane. Even the oceans release methane, produced by microorganisms living in seafloor sediments. Without life constantly replenishing it, Earth's atmospheric methane would disappear in about a decade. The same principle applies to K2-18b. The levels of methane Webb detected are far higher than geological processes alone could explain. something must be producing that methane. And the most likely something, statistically speaking, is life. But methane alone isn't proof of biology. Geological processes can produce methane. Volcanic activity, reactions between rocks and water at high temperatures and pressures, impacts of methane-rich comets. Scientists carefully considered these alternatives. Could K2-18b have active volcanism pumping methane into the atmosphere? Possibly, but there was no evidence of volcanic activity. The planet's atmosphere didn't show the sulfur dioxide or other volcanic gases you'd expect from active volcanism. Could hydrothermal vents in a subsurface ocean be producing methane through chemical reactions? Perhaps, but in quantities large enough to explain Webb's observations? That seemed unlikely. What made K2-18b's detection so compelling wasn't just the methane. It was the combination, methane and carbon dioxide together, in an atmosphere with abundant water vapor, on a planet in the habitable zone with conditions that could support liquid water on the surface or in the atmosphere. And there was something else, something that, when the scientific teams saw it in the data, made hearts race and forced them to triple-check their analysis. A possible detection of dimethyl sulfide. Dimethyl sulfide, or DMS, is a sulfur compound with the chemical formula CH3.2S. It smells terrible, like rotting cabbage. On Earth, it's produced primarily by phytoplankton, microscopic photosynthetic organisms that drift in the oceans. When phytoplankton are stressed, dying, or being consumed by other organisms, they release DMS as a byproduct. The gas rises from the ocean into the atmosphere. Here's the crucial point. Scientists know of no significant non-biological source of DMS. Unlike methane or even oxygen, which can be produced by geological or photochemical processes under certain conditions, DMS appears to be almost exclusively a signature of life. If DMS is present on K2-18b, if the detection is confirmed with additional observations, it would be the strongest evidence of extraterrestrial life ever obtained. The probability of DMS existing in planetary atmospheres without biology is so low that its confirmed presence would essentially prove life exists there. The DMS detection is preliminary. Spectroscopic detections at the edge of instrument sensitivity are always tentative. DMS shares some spectral features with other sulfur compounds. The signal could be noise. It could be another molecule entirely. More observations are absolutely necessary before we can be certain. But the preliminary data is tantalizing. More than tantalizing. It's revolutionary. Based on the atmospheric composition, the planet's mass and radius, and modeling of interior structure, scientists have developed a working hypothesis about K2-18b's nature. They believe it might be a Hycean world, a new class of potentially habitable planet identified in recent theoretical work. Hycean planets, a name combining hydrogen and ocean, are thought to be water worlds with hydrogen-rich atmospheres. They're larger than Earth but smaller than Neptune. The surface, if you can call it that, would be entirely covered by a global ocean hundreds of miles deep. Beneath that ocean, extreme pressure would create exotic forms of ice, different crystal structures that exist only under immense pressure. Deeper still, a rocky core, possibly molten. Above the ocean, atmosphere, thick and dense, dominated by hydrogen with water vapor, methane and other gases mixed in. The atmospheric pressure at the ocean surface would be much higher than on Earth, perhaps dozens or hundreds of times greater. The hydrogen atmosphere would act as a greenhouse, trapping heat and maintaining warm temperatures even at K2-18b's distance from its star. If this model is correct, K2-18b looks nothing like Earth. There are no continents, no land masses, no mountains or valleys, just ocean, stretching from pole to pole, dark and deep beneath a sky thick with clouds and haze. The temperature is estimated around 120 degrees Celsius, based on the planet's orbital distance and atmospheric modeling. That's warm, warmer than Earth's average, but far from boiling. Many ecosystems on Earth thrive at similar or higher temperatures. Hot springs in Yellowstone National Park reach temperatures exceeding 200 degrees Celsius. Yet they teem with thermophilic bacteria adapted to those extreme conditions. If K2-18b has oceans at 120 degrees, they could be incredibly productive. Warm water holds less dissolved oxygen than cold water, but if the life there doesn't depend on oxygen, that wouldn't matter. The metabolism could be entirely different from Earth's. Anaerobic organisms deriving energy from chemical reactions that don't require oxygen. Photosynthetic organisms using the filtered orange light from K2-18's star to power their biology. The statistical confidence is staggering. Based on the atmospheric chemistry, particularly the methane levels and the tentative DMS detection, scientists estimate the probability that biological processes are at work on K2-18b at 99.7%. Not certainty. Science doesn't traffic in absolute certainty, but 99.7% is as close as we can get while maintaining scientific rigor. Think about that number, 99.7%. If you heard that there was a 99.7% chance of rain tomorrow, you'd carry an umbrella without question. If a medical test had 99.7% accuracy, you'd trust the result. 99.7% isn't proof, but it's overwhelmingly compelling evidence. We may have found life, not definitive, incontrovertible proof, not yet, but evidence so strong that the burden of proof has shifted. The question is no longer, does life exist on K2-18b, but what alternative explanation could possibly account for these observations? And so far, no one has found a convincing alternative. More observations are planned. Webb will study K2-18b again, collecting more transits, refining the spectroscopic measurements, attempting to confirm the DMS detection with higher confidence. Other exoplanets will be studied for comparison. Theoretical models will be refined. Laboratory experiments will test whether there are unknown chemical processes that could produce the observed atmospheric composition without biology. But right now, with the data we have, with the analysis completed by some of the best scientific minds on Earth, the most likely explanation for what we're seeing on K2-18b is life. We stand at a threshold. For the first time in human history, we're not just wondering about life beyond Earth. We're analyzing the evidence, calculating the probabilities, and approaching something very close to certainty. A planet 120 light-years away orbiting an unremarkable star in the constellation Leo may be home to organisms that evolved independently from us, that adapted to conditions unlike anything on Earth, that are living their lives right now, completely unaware that we've noticed them across the cosmic void. If this is true, if life exists on K2-18b, then the implications are staggering. Life is not unique to Earth. The processes that led to biology here, the chemistry, the evolution, the gradual complexification from simple molecules to self-replicating systems, to the rich diversity we see around us, those processes are not miraculous accidents. They're natural consequences of physics and chemistry operating under the right conditions. And if it can happen twice, it can happen billions of times. The universe may not be lonely at all. It may be teeming with life, with biospheres evolving in isolation on countless worlds, each one a unique experiment, each one precious and irreplaceable. We've found one possible example, the first, but it won't be the last. The search has only just begun. Throughout human history, we've wondered what alien life might look like. Science fiction has given us endless varieties, little green men with bulbous heads and large eyes, insectoid hive minds driven by collective consciousness, crystalline entities that think in timescales of millennia, energy beings that exist as patterns of pure thought, silicon-based organisms that breathe nitrogen and drink liquid methane. The reality, at least for the first confirmed extraterrestrial life, is likely to be far more humble, far less dramatic, but no less profound. Microbes, single-celled organisms. Perhaps colonies of bacteria-like creatures living in the oceans of K2 to 18b, invisible to any telescope, detectable only by the chemical waste products they pump into the atmosphere as they metabolize and reproduce. And yet, that would be enough. That would be everything. The biosignatures detected on K2-18b tell a story. Each molecule is a clue, a piece of a puzzle that, when assembled, points toward life. Let's examine each one in detail and understand why these chemicals matter so profoundly. Methane is the simplest biosignature, yet also one of the most compelling. On Earth, methane enters the atmosphere through multiple pathways. Wetlands are the single largest natural source. In oxygen-depleted swamp water, methane-producing microbes called methanogens break down organic matter, releasing CH4 as a byproduct. These organisms are ancient, among the earliest forms of life on Earth, and they thrive in environments where oxygen would kill them. Rice paddies, essentially. Artificial wetlands produce enormous quantities of methane. The waterlogged soil creates anaerobic conditions perfect for methanogens. Livestock, particularly ruminants like cows and sheep, have methanogens living in their digestive systems. A single cow can produce 500 liters of methane per day. Multiply that by the billions of cattle worldwide, and you have a significant atmospheric source. Termites, tiny as they are, collectively produce substantial methane as they digest wood. Landfills where organic waste decomposes in anaerobic conditions release methane. Even the oceans contribute, with methanogens living in seafloor sediments producing methane that sometimes bubbles to the surface. Geological sources exist too. Natural gas deposits, primarily methane, can seep to the surface through cracks and fissures. Volcanic activity can release methane trapped in Earth's mantle. Hydrothermal vents on the seafloor can produce methane through chemical reactions between water and certain minerals at high temperatures and pressures. But here's the key point. On Earth, biological methane production vastly outweighs geological sources. By some estimates, up to 70–80% of atmospheric methane comes from biological activity. Without life constantly replenishing it, Earth's atmospheric methane would disappear in about 10 to 12 years, broken down by chemical reactions with hydroxyl radicals in the atmosphere and by ultraviolet light from the sun. The same photochemical destruction happens on K2-18b. For methane to persist at the levels Webb detected, something must be producing it continuously. Geological processes alone seem insufficient. The planet shows no evidence of active volcanism. There's no reason to believe K2-18b has uniquely active hydrothermal systems that would produce methane in such quantities. Biology becomes the most parsimonious explanation. Occam's razor. When you have multiple explanations for a phenomenon, the simplest one that accounts for all the observations is usually correct. Carbon dioxide is abundant on many planets. Venus's atmosphere is 96% CO2. Mars is 95% CO2. On Earth, it's just 0.04%, but it plays a crucial role in regulating climate and is essential for photosynthesis. CO2 is produced by volcanic outgassing, by the weathering of rocks, and by the metabolism of living organisms. On K2-18b, the presence of carbon dioxide is unsurprising. It's a common atmospheric constituent. What matters is its ratio relative to other gases, and what that tells us about the planet's chemistry and potential metabolism. The combination of CO2 and CH4 is particularly interesting because these gases can be part of complementary biological cycles. On Earth, methanotrophs, bacteria that consume methane and produce CO2, balance the methanogens that do the reverse. Photosynthetic organisms consume CO2 and produce oxygen. The cycles interlock, creating complex biogeochemical systems that regulate atmospheric composition. If K2-18b has life, similar cycles might operate, though with potentially different chemistry adapted to the planet's unique conditions. Water vapor is the medium of life as we know it. Every biochemical reaction we've studied requires water. It's not just that organisms need water to drink. Water is fundamental to the structure and function of biological molecules. DNA's double helix is stabilized by hydrogen bonds between water molecules. Proteins fold into their functional shapes partly due to interactions with water. Cell membranes are lipid bilayers that form because lipid molecules arrange themselves to minimize contact between their water-repelling tails and the aqueous environment. Water is an excellent solvent, dissolving more substances than any other liquid. This allows it to transport nutrients, remove waste products, and facilitate chemical reactions. Water has a high heat capacity, meaning it can absorb or release large amounts of heat with minimal temperature change, helping organisms regulate their internal temperature. Water expands when it freezes, which is unusual and biologically important because it means ice floats, allowing aquatic life to survive in liquid water beneath frozen surfaces. K2-18b's atmosphere contains significant water vapor. Combined with the planet's position in the habitable zone, this strongly suggests liquid water exists somewhere on the planet, perhaps as a global ocean, perhaps as clouds and rain in the atmosphere, perhaps both. And then there's dimethyl sulfide, the smoking gun. DMS on Earth is produced primarily by phytoplankton, particularly coccolithophores and dinoflagellates. These microscopic organisms drift in the ocean by the billions, performing photosynthesis and forming the base of the marine food web. When they're stressed, eaten by zooplankton, infected by viruses, or dying, they release DMS. The DMS rises from the ocean into the atmosphere, where it plays a surprising role in climate. DMS oxidizes in the atmosphere, producing sulfate aerosols that serve as cloud condensation nuclei. These aerosols help clouds form. More clouds mean more sunlight reflected back to space, cooling the Earth. Some scientists have proposed that this creates a biological climate regulation feedback. When the ocean warms, phytoplankton populations change, altering DMS production and cloud formation in ways that could moderate temperature. The crucial point: we know of no significant non-biological source of DMS. Unlike methane, which can be produced geologically, or oxygen, which can result from photodissociation of water by ultraviolet light, DMS appears to require biology. Laboratory studies have searched for abiotic DMS production pathways. None have been found that could produce DMS in quantities comparable to biological sources. Volcanic emissions contain trace amounts of various sulfur compounds, but not DMS in any significant quantity. Photochemical reactions in atmospheres can produce many molecules, but DMS doesn't appear to be among them under plausible planetary conditions. If DMS is confirmed on K2-18b, the implications are almost inescapable. Something is producing it, that something is almost certainly life. The tentative detection is based on spectral features that match DMS. But spectroscopy at the limits of instrument sensitivity is challenging. Noise in the data can create false signals. Other molecules with similar absorption features could be misidentified. This is why confirmation is essential. Webb will observe K2-18b again. Each additional transit provides more data, reducing uncertainty, allowing scientists to distinguish between real signals and unknown. Other instruments might contribute. The European Extremely Large Telescope, when completed, will have spectroscopic capabilities that could provide independent confirmation. But even with the preliminary data, even with the uncertainties, the scientific community is taking this seriously. Because if true, it would be the most important discovery in the history of science. Are we looking at microbes? Almost certainly. Complex multicellular life took billions of years to evolve on Earth. Single-celled organisms dominated for roughly 3 billion years before the first multicellular life appeared. Intelligence took even longer. Earth is 4.5 billion years old. Homo sapiens emerged only about 300,000 years ago. We've had technology capable of radio transmission for less than 150 years. K2-18b's star is younger than the Sun, about 2 to 3 billion years old. That's enough time for life to emerge, but probably not enough for complex intelligence to evolve, based on Earth's timeline. The life there, if it exists, is probably simple. But simple doesn't mean insignificant. These microbes, if they exist, would prove that life is not unique to Earth. They would demonstrate that the chemical processes that led to life here can occur elsewhere, perhaps commonly. They would suggest that the universe might be filled with biospheres, each evolving in isolation, each adapting to local conditions, each a unique expression of biology's potential. The diversity of life on Earth is staggering. From bacteria living in boiling acidic springs to archaea thriving in Antarctic ice, from deep-sea organisms surviving crushing pressures to microbes colonizing the clouds, life has adapted to every conceivable niche on our planet. If life emerged independently on K2-18b, it has had billions of years to adapt to conditions we can barely imagine. What would that life look like? We don't know. It might use DNA and RNA like Earth life, or it might have evolved entirely different information storage molecules. It might use proteins as enzymes or something else entirely. It might be carbon-based like us, or it might incorporate other elements in ways we haven't considered. The biochemistry could be radically different. On Earth, oxygenic photosynthesis evolved relatively early and has produced the oxygen-rich atmosphere that allows complex life to thrive. But K2-18b might not have significant oxygen. The life there might derive energy from entirely different chemical pathways. Imagine chemosynthetic organisms clustering around hydrothermal vents on the ocean floor, deriving energy from the chemical gradients between hot, mineral-rich vent water and cold seawater. On Earth, such ecosystems exist in perpetual darkness, yet they support rich communities of organisms, from bacteria to tube worms to crabs. K2-18b's ocean might host similar ecosystems, scaled up to planetary size. Or perhaps the thick atmosphere allows enough filtered light to penetrate that photosynthetic organisms have evolved, adapted to the orange glow of their K-type star. They might use different pigments than Earth's chlorophyll, absorbing different wavelengths optimized for their star's spectrum. Perhaps there are floating ecosystems, mats of organisms drifting on the ocean's surface, forming structures kilometers across. Perhaps there are depth-stratified layers with different organisms adapted to different pressure and light regimes. Perhaps there are migratory patterns driven by planetary seasons, organisms moving with currents or vertically through the water column. We're speculating, of course, but that's part of the excitement. For the first time, we're speculating based on evidence rather than pure imagination. We have data, we have atmospheric chemistry, we have a real planet with real conditions where life might actually exist. The probability, as calculated by the scientific teams analyzing Webb's data, is 99.7% that biological processes are responsible for the atmospheric signatures we're seeing. That number is based on the combination of factors: the methane levels, the possible DMS detection, the presence of water vapor and CO2, the planet's position in the habitable zone, and the difficulty of explaining these observations through non-biological processes. 99.7%. It's not absolute certainty, but it's overwhelming evidence. In science, we rarely get absolute proof. We get evidence, probabilities, confidence levels. And 99.7% is about as confident as science gets. More observations will refine that number. Perhaps it will increase to 99.9%. Perhaps it will drop if alternative explanations are found. But right now, based on the best data and analysis available, the most likely explanation for what we're seeing on K2-18b is life. We may have found it. After millennia of wondering, centuries of speculating, decades of searching, we may have actually found evidence of life beyond Earth. Not little green men, not an alien civilization, just microbes, simple organisms carrying out their metabolism, reproducing, perhaps even evolving, completely unaware that their chemical waste products have been detected across 120 light-years of space by a species that only recently learned how to build telescopes. And if we've found life once, how many other times will we find it? How many other planets in our galaxy harbor biospheres? How common is life in the universe? These questions, once purely philosophical, are becoming empirical. We're entering an era where we can actually answer them. One observation, one planet, one biosignature at a time. The cosmos is revealing its secrets. And the first secret it's sharing is this: we are not alone. It's a provocative question, perhaps even heretical to some. How could any world be better than Earth? This pale blue dot, as Carl Sagan called it, has given us everything: breathable air, drinkable water, fertile soil, a climate that has allowed human civilization to flourish for 10,000 years. Earth is paradise, the only planet we've ever known, the only world in the cosmos confirmed to support life. But what if Earth isn't the pinnacle of habitability? What if it's just one example among potentially billions of life-bearing worlds, some of which might offer conditions even more conducive to life than our own? K2-18b presents an intriguing case. Let's examine the evidence and explore whether this distant world might, in certain ways, surpass Earth. First, consider stellar stability. Earth orbits the Sun, a G-type yellow dwarf that has been shining steadily for 4.6 billion years. The Sun is currently in its main sequence phase, fusing hydrogen into helium in its core, a process that will continue for another 5 billion years before the Sun begins to die, swelling into a red giant that will likely engulf Earth. But the Sun isn't perfectly stable over geological time. Its luminosity increases about 10% every billion years. This slow brightening is already affecting Earth. In about 1 billion years, maybe less, the increasing solar output will trigger a runaway greenhouse effect. Earth's oceans will boil away. The planet will become uninhabitable, resembling Venus more than the temperate world we know. K2-18b orbits a K-type orange dwarf, smaller and cooler than the Sun. K-type stars have lifespans of 20 to 50 billion years, far longer than the Sun's 10 billion. They brighten far more slowly over time. A planet in the habitable zone of a K-type star could remain habitable for tens of billions of years, potentially allowing life far more time to evolve, diversify, and develop complexity than life has had on Earth. Time matters enormously for evolution. On Earth, it took roughly 700 million years from the planet's formation for life to emerge. Simple, single-celled organisms dominated for the next 3 billion years. Complex multicellular life didn't appear until about 600 million years ago. Intelligence and technology emerged only in the last few million years. If K2-18b's star is 2 to 3 billion years old and will remain stable for tens of billions more, life there has potentially enormous stretches of time to evolve. If the planet remains habitable for 40 billion years and Earth-like evolution occurs, who knows what complexity might emerge given enough time? Next, consider the global ocean. If K2-18b is indeed a Hycean world, it would be entirely covered by water hundreds of miles deep. No continents, no land masses, just ocean, stretching from pole to pole, unbroken and vast beyond human comprehension. Is that better than Earth's configuration of continents and oceans? For life in general, it might be. Oceans are thermally stable. Water has a high heat capacity, meaning it absorbs and releases heat slowly. This moderates temperature extremes. A global ocean would create a climate far more uniform than Earth's, with no deserts, no extreme temperature gradients, just gentle variations from equator to pole, driven by the planet's tilt and rotation. Weather patterns would be simpler. On Earth, continents disrupt atmospheric circulation, creating complex regional climates. A global ocean planet would have more uniform wind patterns, driven primarily by the planet's rotation and solar heating of the ocean's surface. Deep oceans offer protection from cosmic threats. Asteroid impacts that would devastate a terrestrial planet might barely affect a deep ocean biosphere. The impact energy would be absorbed by water. Surface life might be disrupted, but organisms in the deep ocean could survive and repopulate. Cosmic radiation, solar flares, these threats are mitigated by water. Even relatively shallow ocean depths provide excellent radiation shielding. A deep ocean biosphere would be well protected from the radiation environment that can make life challenging on planetary surfaces. A global ocean also allows for extraordinary connectivity. Ocean currents could link ecosystems across the entire planet. Organisms could migrate across vast distances. Nutrients could be transported globally, preventing the isolated depletion that occurs in some terrestrial environments. Earth's ocean is already the most bioproductive part of our planet. Despite covering 71% of the surface, oceans contain an estimated 50–80% of all life on Earth. Imagine scaling that up. An ocean covering 100% of the surface, potentially hundreds of miles deep, with layers upon layers of ecological niches. Near the surface, where filtered light from K2-18's orange star penetrates the thick atmosphere, photosynthetic organisms might drift. Imagine vast expanses of floating microbial mats, perhaps organized into structures that dwarf Earth's largest kelp forests. These producers would form the base of the food web, capturing solar energy and converting it into organic matter. Below them, in the twilight zone where light fades, filter feeders might dominate, straining the water for organic particles drifting down from above. Predators adapted to dim light conditions might hunt by bioluminescence or chemical sensing rather than vision. Deeper still, in the perpetual darkness, ecosystems could cluster around hydrothermal vents, just as they do on Earth. Chemosynthetic bacteria would form the foundation, deriving energy from chemical reactions between hot, vent water, and seawater. Around them, complex communities might evolve. Organisms feeding on the bacteria, predators feeding on those organisms, and so on up the food chain. The depth of K2-18b's ocean creates an incredible range of pressures. Near the surface, pressure might be dozens or hundreds of times Earth's sea level pressure due to the thick atmosphere. Miles down, pressures could reach thousands of atmospheres. Each pressure regime creates distinct environmental niches, potentially allowing for greater biodiversity than Earth's ocean supports. Earth's biodiversity is staggering. Scientists estimate there are roughly 8 to 10 million species on our planet, though only about 1.7 million have been formally described. The vast majority of this diversity exists in terrestrial environments, tropical rainforests, grasslands, mountains. But that's partly because we've spent more time studying land than ocean. The deep ocean remains largely unexplored. We know more about the surface of Mars than about the deepest parts of Earth's oceans. Every deep-sea expedition discovers new species, new ecosystems, new examples of life adapting to conditions once thought uninhabitable. A planet with a global ocean and billions of years of evolutionary time might support even greater biodiversity than Earth. The connectivity of a global ocean could facilitate gene flow between populations, preventing speciation, but also allowing beneficial adaptations to spread rapidly. Or perhaps the vast scale creates effective isolation despite the connectivity, with distinct ecosystems evolving in different ocean basins or depth zones. What about the atmosphere? K2-18b's atmosphere is likely thick, dominated by hydrogen with water vapor, methane, and other gases. That thickness provides excellent thermal insulation, maintaining warm temperatures even at the planet's distance from its star. It also shields the surface from harmful radiation. Hydrogen atmospheres are unusual from Earth's perspective. Our atmosphere is nitrogen and oxygen with trace amounts of argon, CO2, and water vapor. But hydrogen atmospheres might be common on super-Earths. Hydrogen is the most abundant element in the universe, and larger planets with stronger gravity can retain it more easily than small planets like Earth. Would life struggle in a hydrogen atmosphere? Not necessarily. On Earth, some microorganisms thrive in hydrogen-rich environments. Hydrogen eutrophs use hydrogen gas as an energy source, combining it with CO2 to produce methane or organic matter. If life evolved on K2-18b under a hydrogen atmosphere, it would be adapted to those conditions, just as Earth life is adapted to nitrogen and oxygen. The atmospheric pressure at K2-18b's ocean surface would be much higher than on Earth, perhaps tens or hundreds of times our sea level pressure. High pressure affects chemistry, making some reactions easier and others harder. Life would adapt, developing biochemistry optimized for high-pressure conditions. Could K2-18b support more biomass than Earth? Possibly. A global ocean with a stable climate, abundant water, and steady energy input from its star could be incredibly productive. Earth's ocean produces roughly 50 billion tons of carbon biomass per year through photosynthesis. A larger ocean with more uniform conditions might exceed that. Could it support greater diversity? We can only speculate, but the conditions seem favorable. More time for evolution, more ecological niches across depth gradients, more stable environmental conditions. Could it be more resistant to catastrophic events? In some ways, yes. Asteroid impacts that would cause mass extinctions on Earth might have limited effects on a deep ocean biosphere. Climate changes would be moderated by the ocean's thermal inertia. Even catastrophic stellar events like flares, which K-type stars can produce, would have reduced impact on organisms protected by hundreds of meters of water. So, is K2-18b better than Earth? That depends on perspective. For humanity, absolutely not. We could never live there. The gravity, roughly 2.6 times Earth's, would make movement exhausting. Standing upright would be a struggle. Over time, the constant gravitational strain would damage our bones, hearts, and circulatory systems. The atmospheric composition would kill us within minutes. The heat and pressure would make the environment utterly hostile to human life. But for life in general, for the raw potential to support biology in all its diverse forms, K2-18b might offer advantages Earth doesn't have. The sky of K2-18b would be alien and beautiful. The thick atmosphere would scatter light in unfamiliar ways, perhaps creating a perpetual haze. The star K2-18, cooler and redder than our Sun, would cast the world in a warm orange glow, very different from Earth's yellow-white sunlight. Sunsets might last for hours as the star's light refracted through the atmospheric layers, painting the sky in gradients of orange, red, and purple. Clouds, if they exist, might be made of water vapor like Earth's, or they might contain exotic compounds produced by the atmospheric chemistry. Lightning could flash through the clouds, driven by atmospheric dynamics we don't fully understand. Storms might rage, but without continents to disrupt them, weather systems could circulate the planet in vast, organized patterns. And the ocean. Imagine standing on the surface, if such a thing were possible. Water stretching to every horizon, the curvature of the planet visible in the distance. Waves rolling endlessly, driven by winds circling the globe. Beneath your feet, not meters but hundreds of kilometers of depth, teeming with life. Currents swirling, carrying nutrients and organisms across hemispheres. A world in constant motion, alive in ways we can barely fathom. Earth is our home. It's the only planet we can actually experience, the only world where we can breathe the air and drink the water and walk on solid ground. Earth is irreplaceable to us, precious beyond measure. But K2-18b reminds us that the universe is vast and full of possibilities. Our planet is unique in our experience, but it may not be unique in the cosmos. There may be many Earths out there, each different, each adapted to its local conditions, each potentially harboring life. Some might be harsh, barely habitable, life clinging to existence in marginal environments. Others, like K2-18b, might be oases, worlds where conditions are not just adequate for life, but optimal, allowing biospheres to flourish and diversify over billions of years. Better is subjective. Earth is perfect for us because we evolved here. But for life in general, K2-18b might represent a different kind of paradise. A water world where evolution has had deep time to work its magic, creating wonders we've never imagined. And we're only beginning to discover these worlds. K2-18b is one example among thousands of known exoplanets and potentially billions of undiscovered ones. Each one tells a different story about how planets form, evolve, and potentially support life. The diversity of worlds in our galaxy may rival or exceed the diversity of life on Earth. Rocky planets and ocean worlds, planets with methane lakes and planets with clouds of iron, worlds orbiting twin stars and worlds wandering alone through interstellar space. Each one unique, each one a possibility. Earth is our home and it always will be. But K2-18b shows us that the universe contains multitudes, and some of those worlds might be even more extraordinary than our own. When Nicholas Copernicus proposed that Earth orbits the Sun rather than sitting at the center of creation, he didn't just challenge astronomy. He challenged humanity's understanding of our place in the cosmos. For millennia, humans had believed we occupied the center of everything, that the heavens literally revolved around us. Copernicus shattered that comforting illusion. We were displaced from the center, made to orbit like every other planet. The reaction was fierce. Religious authorities condemned the idea as heretical. Philosophers struggled to reconcile it with long-held beliefs about human significance. Even many scientists resisted, clinging to the geocentric model because it felt right, because it aligned with our intuitive experience of standing still while the sun and stars move across the sky. But eventually, evidence won out. Galileo's telescopic observations of Venus's phases, which could only be explained if Venus orbited the Sun, provided compelling support. Johannes Kepler's mathematical laws of planetary motion described elliptical orbits around the Sun with extraordinary precision. Isaac Newton's theory of gravitation explained why planets orbit stars and moons orbit planets. The heliocentric model wasn't just correct, it was elegantly, powerfully, demonstrably true. Humanity adapted. We learned to live with our displacement from the cosmic center. And in that displacement, we found something unexpected. Not diminishment, but liberation. If Earth isn't the center of everything, then perhaps the universe is bigger, stranger, and more wonderful than we'd imagined. When Charles Darwin published On the Origin of Species in 1859, he triggered another revolution. Darwin didn't just explain the diversity of life on Earth, he redefined our relationship to that life. We weren't specially created, separate from nature, made in the image of a creator. We were part of an unbroken chain of evolution stretching back billions of years, connected to every organism on Earth through common ancestry. Again, the reaction was fierce. Religious authorities condemned evolution as atheistic. Social commentators worried about the moral implications of being descended from apes. Scientists debated the mechanisms and evidence. But again, over time, the evidence became overwhelming. Fossil records, comparative anatomy, embryology, and eventually genetics all confirmed that evolution through natural selection is the organizing principle of biology. And again, humanity adapted. We learned to see ourselves as part of nature rather than separate from it. We gained deeper understanding of our origins, our biology, our relationship to the ecosystems that sustain us. Darwin's revolution, like Copernicus's, displaced us from a position of presumed centrality, but it also revealed profound truths about the nature of life. The discovery of life beyond Earth would be a Copernican revolution for our age, perhaps even greater in its implications than either of those earlier upheavals. For thousands of years, many human cultures have believed Earth to be special, unique, the only world blessed with life. Theological traditions across the globe have centered on the idea that humanity occupies a privileged position in creation, that we are the purpose of existence, that the cosmos was made for us. If life exists on K2-18b, that belief becomes untenable. We are not special. We are not unique. We are one example among potentially billions. Life is not a miracle confined to Earth. It's a natural phenomenon arising wherever conditions allow. This might feel like a loss. It might feel like yet another displacement, another diminishment of human significance. But consider what it actually means. If life arose independently on K2-18b, then the processes that led to life, the chemistry, the self-organization, the emergence of self-replicating molecules, are not miraculous accidents. They're natural consequences of physics and chemistry operating under the right conditions. That means life might be common, perhaps even abundant throughout the universe. The galaxy contains at least 100 billion stars. Conservative estimates suggest that 50% of those stars have rocky planets in their habitable zones. That's tens of billions of potentially habitable worlds in our galaxy alone. If even a small fraction, say 1%, actually develop life, we're talking about hundreds of millions or billions of life-bearing planets in the Milky Way. And there are trillions of galaxies in the observable universe, each potentially containing billions of life-bearing worlds. The numbers become almost meaningless, so vast they exceed human comprehension. The implications are staggering. Across the cosmos, on worlds we'll never see, beneath alien skies and around strange suns, life might be flourishing. Microbes, certainly, but perhaps also more. Perhaps some worlds have given rise to complex ecosystems, to multicellular organisms, to intelligence. How does this change religion? That's a question billions of people will grapple with in different ways. and there's no single answer. Some religious traditions might find confirmation in the discovery. If a creator made life on Earth, why wouldn't that creator seed life throughout the cosmos? The universe's vastness becomes evidence not of emptiness but of abundance, of a creative force that delights in diversity and fills the cosmos with living things. Other traditions might struggle. Sacred texts written in pre-scientific ages when Earth was thought to be the entire world and humanity the only conscious beings would need reinterpretation. What does it mean that humans are made in a creator's image if there are other intelligent beings? What does redemption mean if other species on other worlds have their own spiritual journeys? But religion has adapted before, and it will adapt again. When Copernicus displaced Earth from the cosmic center, some feared it meant God didn't care about us. Eventually, religious thinkers reconciled heliocentrism with faith, recognizing that God's domain was not a physical location, but a spiritual reality. When Darwin revealed our evolutionary origins, some feared it meant we had no souls. Eventually, most religious traditions incorporated evolution into their worldviews, seeing the process as the mechanism through which a creator worked. The discovery of extraterrestrial life would present similar challenges, but also similar opportunities for growth and deeper understanding. Faith and science need not be in conflict. They address different questions. Science asks how things work. Religion asks why they matter. Philosophy faces its own reckoning. The field of astrobiology has already begun grappling with fundamental questions about the nature of life, consciousness, and our responsibilities toward other biospheres. If we confirm life on K2-18b, should we study it? Of course, the scientific value would be incalculable, but how? Do we have the right to send probes that might contaminate that world with Earth microbes? Do we have the right to extract samples, even if doing so might harm native organisms? These aren't hypothetical questions anymore. Planetary protection protocols already govern our solar system missions. We sterilize spacecraft headed to Mars to avoid contaminating potential Martian habitats. We've deliberately crashed the Cassini spacecraft into Saturn rather than risk contaminating potentially habitable moons like Enceladus. But those are our own solar system's worlds. What responsibilities do we have toward biospheres 120 light-years away, which we can barely detect and certainly can't reach with current technology? If K2-18b's life is microbial, perhaps these questions seem less pressing. But what if it's not? What if Webb or future telescopes find signs of intelligence, of technology, of civilizations? The Fermi paradox has puzzled scientists for decades. Enrico Fermi famously asked, "Where is everybody?" If intelligent life is common in the universe, and if some civilizations are millions or billions of years older than ours, why haven't we detected them? Why haven't they visited? Why is the galaxy not obviously teeming with advanced civilizations? Various answers have been proposed. Perhaps intelligent life is far rarer than we think. Perhaps civilizations tend to be short-lived, destroying themselves through war, environmental collapse, or other catastrophes before they can spread across the galaxy. Perhaps advanced civilizations practice isolation, deliberately avoiding contact with younger species. Perhaps they exist on timescales or in forms we can't recognize. The discovery of life on K2-18b might provide clues. If microbial life is common but intelligence is rare, that would suggest evolution faces bottlenecks between simple and complex life, or between complex life and intelligence. If we find many biospheres but no signs of technology anywhere, perhaps intelligence itself is the rare development. Or perhaps civilizations are common but cautious. Perhaps they've learned that broadcasting their presence is dangerous. Perhaps the galaxy has a dark forest quality, where civilizations hide from each other out of fear. Perhaps we're receiving signals but haven't recognized them. Or perhaps interstellar communication operates on principles we haven't discovered. The discovery also reshapes how we think about Earth. For all of human history, Earth has been everything. The entire world, the only world, all that existed. We've often treated it carelessly, as though resources were infinite and consequences didn't matter. If life is common throughout the universe, then Earth is not irreplaceable in the cosmic sense. There are other biospheres, other living worlds, other places where evolution is unfolding its creative possibilities. In one sense, this might reduce Earth's significance, but in another, more important sense, it should increase our sense of responsibility. Earth may be one of many living worlds, but it's our living world. We evolved here. Every human who has ever lived was born here. Our entire history, culture, art, science, everything that makes us human is rooted in this planet. And unlike those distant biospheres we can only observe, Earth is the one we can actually affect. We have the power to protect it or destroy it. We're conducting a massive, uncontrolled experiment with our climate, pumping greenhouse gases into the atmosphere at rates unprecedented in geological history. We're driving species to extinction at rates comparable to past mass extinction events. We're altering ecosystems across the planet. Knowing that other living worlds exist doesn't give us permission to ruin our own. If anything, it should inspire us to be better stewards. Each biosphere is precious, unique, irreplaceable in its specific expression of life's possibilities. Earth's biosphere has taken 4.5 billion years to develop. If we destroy it, no amount of knowledge about K2-18b or any other world will bring it back. The cosmic perspective, understanding our place in the vast universe, can be humbling in the best way. It reminds us that we're small, that our time here is brief, that the universe existed for billions of years before us and will continue for billions of years after we're gone. But it also reminds us that we're part of something larger. We're not isolated accidents in an empty universe. We're participants in a cosmos that is, apparently, alive. We're one expression of life's creativity, one branch on a tree that might have billions of branches on billions of worlds. Carl Sagan spoke beautifully about this cosmic perspective. In his series Cosmos, he reflected on the famous pale blue dot photograph of Earth taken by Voyager 1 from the edge of the solar system. Earth appears as a tiny speck, less than a pixel, suspended in a beam of scattered sunlight. Sagan wrote, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives, on a mote of dust suspended in a sunbeam." He went on, "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known." That was written in 1990, before we knew exoplanets existed, when the search for life beyond Earth was purely speculative. Now, 35 years later, we may have found that life. And Sagan's words resonate even more deeply. We are not alone in the universe, but we are alone on Earth. This pale blue dot, this mote of dust, is still our only home. Knowing that life exists elsewhere should make us treasure it more, not less. The philosophical implications extend to questions of meaning and purpose. If we're not unique, if life arose through natural processes that occur throughout the universe, what does that mean for human existence? Are we less significant? Does our existence have less meaning? Perhaps the opposite is true. Perhaps significance comes not from uniqueness, but from awareness. We are, as far as we know, the only species in the universe capable of understanding that we're part of the universe. We can study distant worlds. We can decode the chemical signatures of alien atmospheres. We can ask questions about our place in the cosmos and, increasingly, answer them. That capacity for wonder, for curiosity, for the pursuit of knowledge, that's what makes us special. Not our biological uniqueness, which we now know we likely don't have, but our consciousness, our ability to reflect on our own existence and seek to understand the cosmos that gave rise to us. Sagan also said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." If life exists on K2-18b, then K2-18b is another way for the universe to know itself. Different from us, perhaps unimaginably different, but connected by the same cosmic heritage, the same physics and chemistry that govern all things. We are not alone, and that realization, far from diminishing us, elevates us. It makes us part of a community, even if that community is scattered across light years, and we may never meet our neighbors. It connects us to something larger than ourselves, larger than our planet, larger than our brief span of existence. The discovery of life beyond Earth is not the end of human significance. It's the beginning of a new chapter in our understanding of what significance means. We're not the center of creation, but we never were. We're not uniquely alive, but that makes life more, not less, precious. We are conscious beings in a cosmos that appears to be filled with life. We are capable of discovering that life, studying it, learning from it, and perhaps someday, if we're wise and fortunate, connecting with it. That's not diminishment. That's transcendence. That's humanity taking its place not as the masters of creation, but as one species among many. All of us riding this vast cosmic wave together, all of us expressions of the universe's fundamental creativity. The philosophical journey ahead will be challenging. We'll need to rethink old assumptions, adapt traditional beliefs, and grapple with profound questions about our nature and purpose. But humanity has always risen to such challenges. We've adapted before. We'll adapt again. And in that adaptation, in that growth, we might find not loss, but gain. Not loneliness, but connection. Not meaninglessness, but a richer, deeper understanding of meaning itself. The cosmos is calling to us. It's showing us that we're part of something vast and wonderful. It's inviting us to step beyond our planetary borders, not physically, not yet, but intellectually and spiritually. We are children of the cosmos, and we're just beginning to discover how many siblings we might have. 120 light years. The distance is easy to state, difficult to comprehend, and, with our current technology, functionally impossible to cross within human timescales. Let's put that distance in perspective. Light travels at 186,282 miles per second, or about 5.88 trillion miles per year. 120 light years equals roughly 705 trillion miles. Written out, 705,000 miles. The Earth's circumference at the equator is about 24,900 miles. You could circle the Earth more than 28 billion times in the distance between us and K2-18b. The distance from Earth to the Sun, 1 astronomical unit, or AU, is about 93 million miles. K2-18b is about 7.5 million AU away. Our fastest spacecraft, Voyager 1, launched in 1977, is currently traveling at about 38,000 miles per hour relative to the Sun. It's the most distant human-made object, now in interstellar space more than 14.5 billion miles from Earth. At its current speed, Voyager 1 would take approximately 2.1 million years to reach K2 18b. That's longer than modern humans have existed as a species. The speed of light is the universe's ultimate speed limit, at least as far as we understand physics. Nothing with mass can reach or exceed it. Even if we could somehow accelerate a spacecraft to a significant fraction of light speed, say 10%, which is far beyond our current capabilities, the journey to K2 18b would still take 1,200 years, 1,200 years. To put that in historical context, 1,200 years ago, it was the year 826 CE. Charlemagne had recently died. The Viking Age was in full swing. The Islamic Golden Age was flourishing. Most of the world's current nations didn't exist. The scientific method hadn't been invented. The Renaissance was 7 centuries in the future. Imagine launching a spacecraft in 826 CE and waiting for it to arrive now, in 2026. That's the timescale we're discussing, so we're not visiting K2 18b, not anytime soon. Probably not ever, at least not with recognizable human travelers making the journey in their lifetimes. But we can still explore it. We can study it. We can learn from it. And if we're ambitious and patient, we might even send our instruments there, if not ourselves. Robotic exploration is humanity's primary method for studying distant worlds. We've sent probes to every planet in our solar system and many of their moons. We've landed rovers on Mars that have operated for years, analyzing rocks, searching for signs of ancient water, studying the Martian climate. We've orbited Jupiter and Saturn, discovering moons with subsurface oceans and geysers that might harbor life. We've sent spacecraft to study comets and asteroids up close. These missions represent triumphs of engineering and patience. The Voyager probes, launched in 1937 to study the outer planets, are still operating 47 years later, still sending back data from interstellar space. The Cassini mission orbited Saturn for 13 years, transforming our understanding of that planet and its moons. The New Horizons probe flew past Pluto in 2015 after a 9-year journey, revealing that distant world in stunning detail for the first time. Could we do something similar for K2 18b? Theoretically, yes. Practically, the challenges are immense and the timescales are daunting. First, propulsion. Conventional chemical rockets, the kind that launch spacecraft from Earth, won't work for interstellar distances. They're too slow and require too much fuel. Getting even a small probe to a significant fraction of light speed would require fundamentally new technologies. Several concepts exist, at various stages from pure speculation to early development. Ion drives use electric fields to accelerate ions, producing small but continuous thrust. They're far more efficient than chemical rockets and are already used on some spacecraft. NASA's Dawn mission used ion propulsion to visit the asteroids Vesta and Ceres, but even advanced ion drives would take millennia to reach K2 for 18b. Nuclear pulse propulsion, originally proposed in Project Orion in the 1950s, involves detonating small nuclear bombs behind a spacecraft and riding the shockwave. It sounds insane, but the physics works. Estimates suggest it could accelerate a spacecraft to perhaps 5 to 10% of light speed. At 10% light speed, the journey to K2 18b would take 1,200 years. Still far too long, but better than millions of years. Solar sails use the pressure of sunlight or powerful lasers to accelerate spacecraft. The Breakthrough Starshot initiative, backed by Yuri Milner and supported by scientists including Stephen Hawking before his death, proposes using ground-based lasers to push tiny spacecraft, essentially microchips with light sails, to 20% of light speed. The target is Alpha Centauri, just 4.3 light-years away, which would take 20 years to reach. Could this approach work for K2 18b? In principle, yes. The spacecraft would need to be tiny, just a few grams, to achieve those speeds with current or near-future laser technology. At 20% light speed, the journey would take 600 years. The data returning to Earth would take another 120 years. Total mission time, 720 years. That's still far longer than human lifespans, but it's at least conceivable that civilization could maintain continuity over such timescales. We have written records going back more than 5,000 years. We have institutions, governments, and religions that have persisted for over a millennium. A 720-year mission is absurdly long by current standards, but not beyond the realm of possibility for a sufficiently committed civilization. Fusion rockets, which would fuse hydrogen or helium to produce thrust, could potentially reach 10–20% of light speed. Fusion power has been 30 years away for the past 60 years, but recent progress in fusion research suggests we might actually achieve it this century. A fusion-powered spacecraft could carry more mass than a laser-pushed solar sail, allowing for better instruments, communication systems, and onboard processing. Antimatter engines are more speculative. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into energy according to Einstein's EIMC2. This is the most efficient energy conversion possible. A spacecraft powered by matter-antimatter annihilation could potentially reach significant fractions of light speed. The problem? We can only produce tiny amounts of antimatter, and storing it without letting it touch normal matter, which would cause immediate annihilation, is extraordinarily difficult. Antimatter propulsion remains firmly in the realm of theoretical physics and science fiction. Even if we solve propulsion, other challenges remain. Any spacecraft traveling for centuries would need to withstand cosmic radiation, micrometeorite impacts, and the slow degradation of materials. It would need an energy source that lasts for the entire journey. Nuclear reactors, perhaps, or if the spacecraft is small enough, just carefully designed electronics that can operate in low-power hibernation mode for centuries. Communication is another challenge. At 120 light-years away, radio signals would take 120 years each way. We'd send a command, "Take a photo of K2-18b." 120 years later, the spacecraft receives it. It takes the photo and transmits it back. 120 years after that, we receive the image. Total time from command to receipt, 240 years. More practically, the spacecraft would need to be largely autonomous, capable of making decisions without waiting for instructions from Earth. It would need sophisticated AI, sensors to detect and respond to problems, and the ability to adapt to unexpected situations. And what would such a probe find if it reached K2-18b? If the planet has life, a robotic explorer could study it in ways Webb never could. Orbiting the planet, it could analyze the atmosphere with instruments far more sophisticated than those on a distant space telescope. It could map the ocean, measuring temperatures, currents, and chemical composition at different depths and latitudes. It could deploy smaller probes to descend through the atmosphere. Imagine a probe descending through K2-18b's thick, hydrogen-rich atmosphere. The pressure builds gradually as it falls. The temperature rises. Sensors measure atmospheric composition, detecting trace gases, analyzing isotope ratios, searching for patterns that indicate biological activity. Lower still, and the probe breaks through the lower cloud layers. If K2-18b has a global ocean, the probe would glimpse it for the first time, a vast, dark expanse of water, stretching to every horizon. The orange light of K2-18, filtered through the thick atmosphere, illuminates the surface in an alien glow. The probe deploys a submersible, a robotic submarine designed to explore the alien ocean. It splashes down and begins to dive. At first, filtered light from above provides some illumination. Sensors detect organic molecules in the water, concentrations higher than would be expected from purely chemical processes. Life signs, deeper. The light fades to twilight, then darkness. The submersible switches to active sonar and chemical sensors. It detects something, a structure, perhaps. A floating mat of organic material kilometers across, teeming with microscopic life. The probe takes samples, analyzing them on site. It identifies cells or cell-like structures. It detects DNA, or something analogous to DNA. It's seeing alien biology firsthand, deeper still. The probe descends for hours, for days, sinking through layers of the ocean. Pressure builds to thousands of atmospheres. Eventually, it detects warmth from below, a hydrothermal vent, spewing mineral-rich water heated by geological processes deep within the planet. Around the vent, an ecosystem, microbial mats coating the rocks, larger organisms feeding on the microbes, predators hunting in the darkness. The probe analyzes, measures, records. It captures images in the light of its own lamps, revealing ecosystems that evolved in complete isolation from Earth, adapted to conditions no terrestrial organism could survive. It transmits data back to the orbiter, which relays it across 120 light-years to Earth. Generations later, centuries after the probe was launched, scientists on Earth receive the transmission. They see images of an alien ocean. They analyze the biology, compare it to Earth life, marvel at the similarities and differences. They learn how life evolved independently on another world, how it adapted to the specific conditions of K2-18b, what universal principles govern biology and what aspects are contingent on local environments. It would be the greatest scientific achievement in human history. And it would be the work not of one generation, but of many. The people who design and launch the probe will be long dead before it arrives. The people who built the rockets and the instruments will be gone. The people who receive the first data will live in a world transformed by challenges and changes we can't foresee. This is the reality of interstellar exploration. It requires patience beyond individual human lifespans. It requires institutional commitment across generations. It requires faith that the pursuit of knowledge is worth the cost, even if those who pay the cost never see the results. Could humans ever visit K2-18b in person? Not as we are. Our biology isn't suited to journeys lasting centuries. We live for decades, perhaps a century with advanced medicine, but not the timescales required for interstellar travel at sublight speeds. Generation ships are a classic science fiction solution. Massive vessels carrying entire communities across the void, with multiple generations born, living and dying aboard the ship before the destination is reached. The engineering challenges are staggering. How do you maintain life support systems for centuries? How do you produce food, recycle air and water, manage waste? How do you prevent social collapse among a crew that will never see their destination? How do you ensure the mission survives equipment failures, accidents, political upheavals, and the psychological toll of confinement? And even if you solve all those problems, you're still looking at a journey of thousands of years to K2-18b with realistic propulsion technologies. Perhaps the answer isn't sending humans as we are, but transforming what humans are. Advanced genetic engineering could extend lifespans dramatically, potentially to centuries or millennia. If aging could be stopped or reversed, if disease could be eliminated, if human bodies could be redesigned for long-duration spaceflight, the timescales become more manageable. Suspended animation or cryogenic freezing could allow travelers to sleep through the journey. Their metabolisms slowed to near zero, aging effectively stopped. wake up centuries later at the destination having aged only days or months. The technology doesn't exist yet, but research continues. Some animals can enter states of suspended metabolism for months or years. If we could replicate that in humans, interstellar travel becomes more feasible. Digital consciousness, uploading human minds to computers, is more speculative but offers intriguing possibilities. If consciousness could exist as software rather than wetware, you could travel as data across the stars. Copy yourself and send the copy on a spacecraft, or even transmit your mind as a radio signal at light speed. The physical body stays behind. The mind arrives in a fraction of the time. These concepts range from plausible to highly speculative to purely fictional. But humanity has a history of turning the impossible into the routine. Powered flight was fantasy until the Wright brothers made it real. Splitting the atom was theoretical physics until Manhattan Project engineers built working reactors and bombs. Editing DNA was science fiction until CRISPR made it straightforward. For now, our exploration of K2-18b will be remote. Telescopes will continue to observe, gathering more data, refining our understanding. Webb will study the planet's atmosphere in even greater detail, searching for additional biosignatures, confirming or refuting the detection of dimethyl sulfide. Future telescopes, more powerful than anything we've built, will push the boundaries of what we can detect. The European Extremely Large Telescope, currently under construction in Chile's Atacama Desert, will have a primary mirror 39 meters across when completed in the late 2020s. It will be able to directly image some exoplanets, capturing actual photographs rather than just spectroscopic data. Imagine seeing a picture of K2-18b, a tiny blue-green dot separated from its star. Pixels of light containing information about oceans and atmosphere and, perhaps, life. NASA is planning the Habitable Worlds Observatory, a flagship mission specifically designed to search for life on exoplanets. It would combine Webb's sensitivity with next-generation optics and instruments optimized for biosignature detection. Launch is tentatively planned for the 2030s or 2040s, depending on funding and technological development. These observations will answer some questions and raise others. Is the DMS detection real? What other biosignatures can we find? Are there seasonal variations in atmospheric composition that might indicate biological cycles? Can we detect oxygen, another strong biosignature, if present with methane? And as our understanding grows, so too will our desire to see K2-18b up close, to send probes, to sample the atmosphere and ocean, to study the life directly rather than through the veil of 120 light-years. That desire will drive technological development. If we want to reach K2-18b, we'll need to invent new propulsion systems, new materials, new approaches to spacecraft design. Those technologies will have applications beyond interstellar exploration. Fusion rockets could revolutionize in-system travel, making trips to Mars or the outer planets routine. Advanced AI developed for autonomous deep space probes could transform robotics here on Earth. Materials science advances needed for century-long missions could lead to better construction materials, more durable infrastructure, longer-lasting products. The journey of 1,000 light-years, or even 100 light-years, begins with a single observation. We've taken that first step. Webb has shown us K2-18b's atmosphere and found tantalizing hints of life. The next steps will be longer, harder, and more audacious than anything we've attempted. But if there's one thing humanity has proven repeatedly, it's that we don't turn away from challenges. We embrace them, we dream the impossible, and then, slowly, patiently, often over generations, we make it real. K2-18b is calling to us across the void, speaking in wavelengths of infrared light, in spectral lines of methane and dimethyl sulfide. It's showing us that life might exist beyond Earth, that the universe is richer and more wonderful than we dared imagine. One day, perhaps, we'll answer that call. We'll send our instruments, our robots, maybe even ourselves. We'll cross the void between stars. We'll see K2-18b with our own sensors or our own eyes. We'll meet the life that evolved there, study it, learn from it, understand how it differs from and resembles the life we know. That day might be centuries away. It might be millennia. But it's coming because we're curious, because we're explorers, because we refuse to accept that the wonders of the cosmos are forever beyond our reach. K2-18b is waiting, and humanity is patient. The discovery on K2-18b is not an endpoint, it's a beginning, a door opening onto a new era of exploration, understanding, and revelation. Over the next decade, our study of K2-18b will intensify. James Webb will continue its observations, collecting data from more transits, refining the spectroscopic measurements, confirming or disproving the tentative dimethyl sulfide detection with higher statistical confidence. Each observation adds clarity, sharpens the picture, and brings us closer to certainty about whether life truly exists on this distant world. But K2-18b is not alone. It's one target among many in Webb's ambitious observing program. Dozens of potentially habitable exoplanets are being studied, each one a candidate for harboring life, each one offering a different perspective on how planets form, evolve, and potentially support biology. Consider the TRAPPIST-1 system, one of the most exciting discoveries in exoplanet science. Just 40 light-years away, closer than K2-18b, this ultra-cool red dwarf star hosts 7 Earth-sized planets in tight orbits. 3 of those planets orbit in the habitable zone, the region where liquid water could exist on their surfaces. TRAPPIST-1 planets are fascinating because they're so close together. The entire 7-planet system would fit inside Mercury's orbit around our Sun. From the surface of any TRAPPIST-1 planet, the other planets would appear as large as the Moon appears from Earth, some even larger. Imagine a sky where neighboring worlds loom overhead, clearly visible as disks rather than points of light, perhaps showing weather patterns and surface features to the naked eye. Webb has already begun studying TRAPPIST-1 planets, analyzing their atmospheres during transits. Early results are intriguing. Some planets show atmospheric chemistry that doesn't match simple, lifeless models. TRAPPIST-1e in particular appears to have an atmosphere and possibly water vapor. More observations are planned throughout the next several years. If TRAPPIST-1e or its neighbors show biosignatures, the implications would be staggering. We'd have evidence of life on not one but multiple exoplanets. We'd know that life isn't just possible but actually exists on worlds very different from Earth, orbiting a star type that dominates the galaxy. Red dwarfs like TRAPPIST-1 make up about 75% of all stars. If planets around red dwarfs can harbor life, then habitable worlds might be incredibly common. Then there's Proxima Centauri b, the nearest exoplanet to Earth at just 4.24 light-years away. It orbits in the habitable zone of Proxima Centauri, the closest star to our Sun. Proxima b is a rocky world, possibly with an atmosphere, possibly with water. But its star is problematic. Proxima Centauri is a red dwarf that flares unpredictably, bombarding nearby planets with intense radiation and charged particles. Could life survive such conditions? We don't know. Earth's magnetic field protects us from solar radiation. If Proxima b has a strong magnetic field and a thick atmosphere, it might be shielded enough for life to persist. Or perhaps life there has evolved robust DNA repair mechanisms. able to survive radiation levels that would sterilize Earth's surface. Proxima b is close enough that future missions could reach it within a human lifetime if we develop sufficiently advanced propulsion. It's a prime target for the Breakthrough Starshot initiative, which aims to send tiny light-sail probes to Alpha Centauri at 20% of light speed. A 20-year journey to our nearest stellar neighbor. If successful, it would be humanity's first venture to another star system. New telescopes are coming online that will revolutionize our ability to study exoplanets. The European Extremely Large Telescope, or ELT, is under construction on Cerro Armazones in Chile's Atacama Desert, one of the driest places on Earth and consequently one of the best locations for ground-based astronomy. When completed in the late 2020s, the ELT will have a primary mirror 39 meters across, making it the largest optical and infrared telescope ever built. The size matters enormously. Light collecting power scales with the square of the mirror diameter. The ELT's mirror will be 6 times wider than Webb's, giving it 36 times more light collecting area. That translates to the ability to see fainter objects, resolve finer details, and collect data much faster than smaller telescopes. The ELT will be able to directly image some exoplanets, capturing actual photographs of worlds orbiting other stars. For decades, we've detected exoplanets indirectly through transits and radial velocity measurements. Direct imaging reveals the planet as a separate point or even disk of light, allowing us to study it without waiting for transits. Imagine seeing a photograph of K2 through 18b. A tiny dot of light, perhaps blue-green from its ocean and atmosphere, clearly separated from its orange star. Spectroscopic analysis of that direct light could reveal details about cloud cover, surface composition, and atmospheric chemistry with precision far exceeding transit spectroscopy. The ELT will also enable high-resolution spectroscopy of exoplanet atmospheres, potentially detecting biosignatures in planets too far or too small for Webb to study effectively. It will search for the red edge, a sharp increase in reflectivity at near-infrared wavelengths caused by Earth plant chlorophyll reflecting light they can't use for photosynthesis. Alien photosynthesis might use different pigments, creating different spectral signatures, but the principle is the same. Life harvesting energy from starlight leaves detectable traces. NASA is planning the Habitable Worlds Observatory, or HWO, a flagship mission specifically designed to search for life on exoplanets. It's still in the early planning stages, with launch tentatively scheduled for the 2030s or 2040s. The exact design isn't finalized, but the mission requirements are clear. Detect and characterize potentially habitable exoplanets, and search for biosignatures with unprecedented sensitivity. HWO would likely use a large primary mirror, possibly 6 to 8 meters across, optimized for visible and ultraviolet light, where Earth-like biosignatures are strongest. It would employ a coronagraph or star shade to block the star's light, allowing it to directly image planets that would otherwise be lost in the star's glare. The ability to separate planetary light from stellar light enables detailed spectroscopy and potentially even crude imaging that could distinguish continents from oceans on distant worlds. The mission could study dozens or hundreds of potentially habitable planets, searching for oxygen, methane, water vapor, and other biosignature combinations. It could detect seasonal variations in atmospheric composition that might indicate biological cycles. It could search for technosignatures, industrial pollutants, city lights on the night side of planets, or other evidence of technological civilizations. Closer to home, missions to our own solar system's potentially habitable moons are launching or in development. Europa, a moon of Jupiter, has a subsurface ocean beneath a shell of ice kept liquid by tidal heating from Jupiter's gravity. geysers erupt from cracks in the ice, spewing water into space. NASA's Europa Clipper mission launched in October 2024 and will arrive at Jupiter in 2030. Europa Clipper won't land on the Moon. Instead, it will make dozens of close flybys, using a suite of instruments to study the ice shell, analyze the composition of the geysers, map the ocean beneath, and determine whether Europa's ocean could support life. The spacecraft carries ice-penetrating radar to measure the ice shell's thickness, spectrometers to analyze surface composition, and magnetometers to characterize the subsurface ocean through its magnetic signature. If Europa Clipper finds compelling evidence that the subsurface ocean is habitable, a follow-up mission could attempt to land and drill through the ice, deploying a submarine to explore the ocean directly. Such a mission would be extraordinarily challenging, but potentially revolutionary. We could study an alien ocean without traveling light years from home. Enceladus, a small moon of Saturn, also has a subsurface ocean and dramatic geysers at its south pole. The Cassini spacecraft flew through those geysers, analyzing their composition and detecting complex organic molecules, salts indicating a salty ocean, and even molecular hydrogen, a potential energy source for life. Enceladus is smaller and has a thinner ice shell than Europa, potentially making it easier to access the subsurface ocean. Several proposed missions aim to return to Enceladus with instruments specifically designed to search for biosignatures in the geyser plumes. A spacecraft could fly through the plumes repeatedly, collecting samples and analyzing them for amino acids, lipids, or other complex organic molecules that might indicate biological origin. We could potentially detect life in Enceladus's ocean without even landing, simply by analyzing what the Moon is already ejecting into space. Titan, Saturn's largest moon, is another fascinating target. It's the only moon in the solar system with a thick atmosphere, actually denser than Earth's, composed primarily of nitrogen with methane and other hydrocarbons. Titan's surface is covered with lakes and rivers, but they're not water. They're liquid methane and ethane, hydrocarbons that are gases on Earth, but liquids in Titan's frigid environment, where surface temperatures average 290 degrees Celsius. Could life exist in liquid methane? We don't know. All life on Earth requires liquid water, but that might reflect our biochemistry rather than a universal requirement. Some scientists have speculated about methane life, organisms using methane as a solvent instead of water, with entirely different chemistry. It's highly speculative, but Titan offers a chance to test the idea. Titan also has a subsurface ocean of water beneath its icy crust, similar to Europa and Enceladus. If that ocean communicates with the surface through cryovolcanism, it might provide another potential habitat for life. NASA's Dragonfly mission, a nuclear-powered drone designed to fly through Titan's thick atmosphere and explore multiple locations on the surface, is scheduled to launch in 2028 and arrive in the mid-2030s. Dragonfly will analyze surface composition, search for complex organic molecules, and study the prebiotic chemistry occurring in Titan's atmosphere and on its surface. While Dragonfly isn't specifically designed to detect life, it will search for the building blocks and chemical signatures that might indicate prebiotic processes or even biosignatures. These solar system missions complement exoplanet observations. Studying Europa, Enceladus, and Titan teaches us about the diversity of potentially habitable environments and expands our understanding of where life can exist. That knowledge informs our search for life on exoplanets and helps us interpret the biosignatures we detect. We're also developing new techniques for detecting biosignatures and refining our understanding of what constitutes convincing evidence of life. Scientists study extremophiles on Earth, organisms that thrive in conditions once thought uninhabitable, boiling acidic springs, frozen Antarctic lakes, deep underground in rock formations, high radiation environments near nuclear reactors. Each extremophile expands our conception of habitability and suggests new biosignatures to search for. Thermophiles that live at temperatures exceeding 200 degrees produce unique heat shock proteins. Halophiles adapted to high salt environments have distinctive membrane chemistry. Radiation-resistant organisms like Deinococcus radiodurans have robust DNA repair mechanisms that might leave detectable chemical signatures. By understanding how life adapts to extreme conditions on Earth, we can better predict what biosignatures might appear in exoplanet atmospheres, with conditions very different from Earth's surface. Laboratory experiments are recreating the conditions of early Earth and other planetary environments, mixing simple chemicals and applying energy to see if the building blocks of life can form spontaneously. The Miller-Urey experiment in 1953 famously demonstrated that amino acids, the building blocks of proteins, can form from simple gases and electrical discharges mimicking lightning. Modern experiments have extended this work, showing that nucleotides, the building blocks of DNA and RNA, lipids, the building blocks of cell membranes, and other essential biomolecules can form under various prebiotic conditions. These experiments help us understand abiogenesis, the origin of life from non-living matter. The better we understand how life begins, the better we can predict where and how it might arise elsewhere. We can estimate how common the necessary conditions are, how long it typically takes for life to emerge, and what chemical signatures early life produces. All of this points toward a future where the discovery of life beyond Earth is not a singular event, but a recurring revelation. K2-18b might be the first confirmed detection, but it won't be the last. Over the next decade, we'll study dozens of exoplanets with increasing sophistication. We'll explore our own solar system's ocean worlds with robotic explorers. We'll refine our theoretical understanding of what life requires and how to detect it. Each discovery will raise new questions. How diverse is life in the universe? Does it always use DNA and proteins, or are there fundamentally different biochemistries? How common is complex multicellular life versus simple microbes? How often does intelligence evolve? How long do civilizations typically last? These questions will define the next century of science. And we're living at the moment when those questions transition from philosophy to empirical investigation. We're gathering data. We're testing hypotheses. We're moving from "I wonder if" to "our observations show that." The pace of discovery is accelerating. In 1995, we confirmed the first exoplanet around a sun-like star. Today, we know of over 5,000 confirmed exoplanets. In another decade, that number might exceed 10,000 or 20,000. Among those thousands, how many will show biosignatures? How many will host life? We don't know yet, but we're going to find out. The next 10 years will be extraordinary. Webb will continue its observations, revealing more about K2-18b and dozens of other worlds. The ELT will come online, adding ground-based capabilities that complement Webb's space-based observations. TRAPPIST-1 planets will be characterized in detail. Proxima b might reveal whether life can survive around active red dwarfs. Europa Clipper will tell us if Jupiter's moon has a habitable ocean. Dragonfly will explore Titan's alien chemistry. And somewhere in that decade, we might find another world with biosignatures, or several worlds, or dozens. We might discover that life is common, that the galaxy is filled with biospheres evolving independently on countless worlds. Or we might find that K2-18b is unusual, that life is rare, that the conditions required are more stringent than we thought. Either way, we'll learn, We'll refine our understanding. We'll answer questions that have puzzled humanity for millennia. This is the golden age of astrobiology. We're living through a period of discovery that future generations will study in awe. The way we study the age of exploration when European sailors first circumnavigated the globe, or the space age when humans first left Earth's surface. Centuries from now, students will learn about the discovery of life on K2-18b, the way we learn about the discovery of the Americas or the first photographs of Earth from space. They'll see it as a turning point, the moment when humanity realized we were not alone, when the universe revealed its abundance, when we understood that life is not a miraculous accident confined to one lucky planet, but a natural consequence of cosmic chemistry playing out across billions of worlds. We get to witness that turning point. We get to be the generation that finds life beyond Earth. That's not a small thing. That's everything. Pause for a moment. Step back from the details, the chemistry and spectroscopy, the distances and probabilities. Let the weight of what we've discussed settle into your awareness. Somewhere out there, 120 light years from this pale blue dot we call home, there is a world. Not a lifeless rock tumbling through the void, not a barren ball of ice and stone. A world where, right now, as you process these words, as you exist in this moment, life may be thriving. Organisms we can barely imagine, adapted to conditions utterly unlike Earth, are living their lives. Metabolizing, reproducing, perhaps evolving, completely unaware of us, unaware that across the cosmic ocean we've noticed them, studied them, marveled at their existence. They don't know we're here, looking at them through instruments of almost incomprehensible sophistication, analyzing the light that filtered through their atmosphere 120 years ago. But we know they might be there. And that knowledge, that possibility grounded in evidence and measurement and careful scientific analysis, is profound beyond measure. For all of human history, every person who has ever lived, loved, suffered, and died has done so on this one planet. Every empire that rose and fell, every war fought, every discovery made, every work of art created, all of it happened here, on Earth. The entire human experience, the totality of our species' existence, has been confined to one world. We've looked up at the stars and wondered. Philosophers in ancient Greece debated whether other worlds existed. Medieval scholars speculated about life on the moon. Renaissance thinkers imagined inhabitants of other planets. Science fiction writers populated the galaxy with alien civilizations, some benevolent, some hostile, all reflections of our own hopes, fears, and imagination. But wonder is not knowledge. Speculation is not evidence. Until now, the question of extraterrestrial life has been fundamentally unanswerable with the tools and data available to us. We could believe, we could hope, we could theorize and calculate probabilities, but we couldn't know. K2-18b changes that equation. For the first time, we have actual data, spectroscopic signatures, chemical compositions, statistical probabilities calculated from real measurements. We have evidence that life, real biological life operating according to the same physics and chemistry that governs life on Earth, might exist on another world. Think about what that means. Truly contemplate it. Life is not a fluke. It's not a miraculous accident confined to one cosmically fortunate planet. It's a natural outcome of chemistry and physics operating under the right conditions. It might be common, perhaps even inevitable given enough time and suitable environments. The universe is not a sterile void punctuated by one island of biology. It's a garden vast beyond comprehension where life blooms wherever the conditions allow. Earth is one flower in that garden. K2-18b might be another, And if 2 flowers bloom, then why not billions? Stand outside on a clear night, away from city lights if you can. Look up at the stars. Most of them are too faint to see with the naked eye, drowned out by light pollution or simply too distant. But they're there, hundreds of billions in our galaxy alone, each one a sun, many of them hosting planets. One of those stars, invisible to you, 120 light-years away in the direction of the constellation Leo, is the host of K2-18b. Right now, light from that star is traveling toward Earth. It will arrive in 120 years, carrying information about the planet's atmosphere, its chemistry, its potential life encoded in wavelengths and spectral lines. Someone in the year 2046 will analyze that light, just as we analyze light from 1906 that's arriving today. Time and space are woven together in ways that challenge our intuition. The universe is not a static stage where events play out in neat chronological order. It's a dynamic, evolving 4-dimensional structure where past, present, and future are all relative to one's position and velocity. When we look at K2-18b, we're seeing it as it was 120 years ago. If there are organisms on K2-18b capable of detecting Earth, they're seeing our planet as it was in 1906. We exist in each other's past. The present moment, the now that feels so immediate and real, is actually a sphere of simultaneity that expands at the speed of light. Everything beyond that sphere is history, frozen in the light currently traveling toward us. This cosmic perspective, this understanding of our place in the vast universe, is humbling in the best possible way. When you realize that Earth is one small planet orbiting one ordinary star in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, it puts our daily concerns into perspective. The arguments that feel so important, the divisions that seem so fundamental, the conflicts that dominate our news cycles and political discourse, all of it shrinks to insignificance against the backdrop of cosmic time and space. But this perspective is also empowering, because we, tiny and fragile as we are, have the capacity to understand all of that vastness. We can decode the light from distant worlds. We can calculate the age of the universe. We can peer back to the cosmic dawn and forward to the heat death of all things. We can ask questions that span billions of years and billions of light years, and increasingly, we can answer them. No other species on Earth can do that. No other organism we know of has developed the technology, the science, the curiosity to reach across the void and study distant worlds. We are, as far as we know, the universe's way of understanding itself, matter organized in such a way that it can contemplate its own existence. And maybe, just maybe, we're not the only ones. Somewhere on K2-18b or on another world orbiting another star, there might be organisms asking the same questions, looking up at their sky, wondering if they're alone, building their own telescopes, detecting their own exoplanets, searching for signs of life beyond their world. Perhaps one day we'll find each other. Perhaps we'll communicate across the light years, share knowledge, learn from one another's unique evolutionary paths and cultural developments. Perhaps we'll discover that intelligence is common, that the universe is full of civilizations at various stages of development, each one asking the same fundamental questions about existence and meaning. Or perhaps the distances are too vast, the timescales too long, and we'll remain forever isolated, knowing we're not alone but unable to reach out and touch, to communicate in real time, to truly connect. Perhaps we'll detect evidence of other civilizations but never meet them, ships passing in the cosmic night, separated by distances and times that make interaction impossible. Either way, the knowledge that life exists beyond Earth changes us fundamentally. It makes us part of something larger than ourselves, larger than our planet, larger than our brief span of existence. It connects us to a cosmic community of living worlds, each one precious, each one unique, each one an expression of the universe's fundamental creativity. Carl Sagan spoke beautifully about this cosmic perspective, about the way understanding our place in the universe changes how we see ourselves and our world. He looked at the pale blue dot photograph, Earth from the edge of the solar system, and saw not insignificance but responsibility, not loneliness but connection, not meaninglessness but profound meaning in our capacity to understand and appreciate the universe that gave rise to us. Sagan said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Every atom in your body was forged in the heart of a dying star billions of years ago. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created by nuclear fusion in stellar cores and scattered into space when those stars exploded as supernovae. You are literally made of star stuff. Ancient matter recycled through cosmic processes and temporarily organized into the pattern we call a living being. If life exists on K2-18b, those organisms are made of the same star stuff. Different atoms forged in different stars, organized according to different biochemical principles adapted to different environmental conditions. But fundamentally, we're cousins, all of us products of the same universe, governed by the same physical laws, built from the same periodic table of elements. We are not alone. And that's not a loss of human significance. It's a gift, an invitation to see ourselves as part of a grander story, one written in starlight and chemistry, in evolution and time, in the endless creativity of a universe that appears to be alive with possibilities. The universe is not silent. It's singing in wavelengths of light, in chemical signatures, in the endless dance of matter and energy across cosmic scales. And we're learning to listen. We're decoding the messages. We're understanding the language. K2-18b is speaking to us across 120 light years and 120 years of light travel time, speaking in the vocabulary of methane and dimethyl sulfide and water vapor. It's telling us that life exists, that the universe is richer than we dared imagine, that we are part of a community we're only beginning to discover. That's not just science, that's poetry. That's the human spirit reaching out across the void, refusing to accept that we're alone, asking questions and demanding answers, using reason and evidence and patient observation to unlock the secrets of the cosmos. We are the inheritors of a legacy that stretches back through all of human history, through all the scientists and philosophers and dreamers who wondered about the stars. We stand on their shoulders, using tools they could barely imagine, answering questions they could only speculate about. And we're passing that legacy forward. The discoveries we're making today will inspire future generations. Children being born now will grow up in a world where extraterrestrial life is not speculation, but confirmed fact. They'll study astrobiology in school. They'll see images from missions to Europa or Enceladus showing alien oceans. They'll watch data come back from interstellar probes launched decades or centuries earlier. They'll look back at us, at this moment, the way we look back at Galileo pointing his telescope at Jupiter's moons, or Darwin collecting specimens in the Galapagos, or Hubble discovering that the universe extends far beyond our galaxy. They'll see us as pioneers, the first generation to find evidence of life beyond Earth. That's our privilege, that's our responsibility, and that's our gift to the future. So take a moment, feel the awe, let it wash over you without trying to analyze or contain it. We live in an age of miracles disguised as science, of wonders revealed through patient observation and careful measurement. We've sent our instruments across the solar system and beyond. We've decoded the human genome. We've photographed black holes. We've detected gravitational waves from colliding neutron stars billions of light years away. And now, we've found evidence of life on another world. That's not just an achievement. It's a revelation. It's the universe opening up to us, showing us its secrets, inviting us to understand the profound truth that we are part of something vast and beautiful and incomprehensibly complex. The universe is not empty. It's not dead. It's alive, or at least it has the capacity for life, the conditions that allow chemistry to become biology, matter to become mind. And we're here to witness it, to understand it, to marvel at it, and to pass that knowledge forward to those who come after us. Welcome to the cosmic community. We're just beginning to understand what that means. We've journeyed together across 120 light years and billions of years of cosmic time. We've explored the history of our search for life, traced the development of exoplanet science from its beginning to this present moment of extraordinary discovery. We've examined the science of habitability, learning what makes a world capable of supporting life. We've marveled at the technology of the James Webb Space Telescope, an instrument so sophisticated it can analyze the atmospheric chemistry of worlds in other star systems. We've studied K2-18b in detail, its location in the constellation Leo, its orange dwarf star, its position in the habitable zone, its atmosphere rich with water vapor, methane, carbon dioxide, and the tantalizing possible detection of dimethyl sulfide. We've calculated the probabilities and found them overwhelming. A 99.7% chance that biological processes are responsible for the atmospheric signatures we're observing. We've contemplated whether K2-18b might be, in some ways, even better suited for life than Earth, with its global ocean, stable climate, and long-lived star. We've grappled with the philosophical implications of finding life beyond our planet, the way this discovery challenges our assumptions about human significance and our place in the cosmos. We've considered the practical challenges of exploration, the vast distances and timescales involved, and the technologies we might develop to reach across the void between stars. We've looked ahead to the next decade of discovery, to new telescopes and new missions, to TRAPPIST-1 and Proxima b and Europa, and Enceladus and Titan, to a future where evidence of life beyond Earth becomes not a singular revelation, but a growing catalogue of biospheres, each one unique, each one precious. But this isn't the end of the story. It's barely the beginning. Every answer we find raises new questions. Every discovery opens new frontiers. K2-18b might host life, but what kind? How did it originate? What does its biochemistry look like? How has it evolved over billions of years? What can it teach us about the fundamental nature of biology, about the conditions that allow life to flourish, about the diversity of forms that life can take? We don't know yet. And that's beautiful, because it means there's still so much to discover, so much to learn, so many worlds waiting to reveal their secrets. Science is not a collection of facts to be memorized. It's a process, a conversation with the universe, where we ask questions and the universe answers not in words but in data, in observations, in the slow, patient accumulation of evidence that brings us incrementally closer to truth. And you're part of that conversation. You, reading or hearing these words, are participating in the same quest that drove ancient astronomers to map the stars, that inspired Galileo to point his telescope at Jupiter, that led to the discovery of exoplanets and the search for life beyond Earth. Curiosity is universal. It's what makes us human. It's what drives us to explore, to question, to seek understanding even when the questions are difficult and the answers uncertain. In an age where information is abundant but attention is scarce, where distractions multiply and compete for every moment of our awareness, nurturing that curiosity is more important than ever. So stay curious, keep asking questions, follow the discoveries as they unfold. James Webb is just getting started. Over the coming years, it will reveal wonders we can't yet imagine. Other telescopes will join the search. The ELT will come online in the late 2020s. The Habitable Worlds Observatory might launch in the 2030s or 2040s. New missions will explore our solar system's ocean worlds. New technologies will emerge, expanding our capabilities in ways we can't predict. And each discovery will be yours to explore, not just through documentaries and articles, but through your own engagement with science. Read the research papers when they're published. Follow the researchers and institutions doing this work. Join the communities of enthusiasts and educators who share your passion for understanding the cosmos. Support science funding and education. Advocate for the missions and instruments that will expand our knowledge. This is the golden age of astronomy, of astrobiology, of cosmic exploration. We're living through a period of discovery that future generations will look back on with envy and wonder. Centuries from now, children will learn about the first detection of life beyond Earth, the way we learn about the discovery of the New World, or the first flight at Kitty Hawk, or the first steps on the moon. And we're here. We get to witness it. We get to be the generation that found evidence of life on K2-18b and perhaps many other worlds. We get to be the ones who looked at the stars and saw not just distant lights, but other suns, other planets, other biospheres where life is unfolding its infinite creative possibilities. That's a privilege, and it comes with a responsibility to stay informed, to support the institutions and individuals doing this work, to advocate for funding for research and exploration, to pass on the wonder and curiosity to the next generation, to children who will grow up in a world where extraterrestrial life is not speculation, but confirmed reality. Because the search for life doesn't end with K2-18b. It continues with TRAPPIST-1, with Proxima b, with Europa and Enceladus, and the thousands of exoplanets we haven't yet discovered. It continues with questions we haven't yet learned to ask, with instruments we haven't yet built, with missions that won't launch for decades. The universe is vast. It's ancient beyond human comprehension. It's complex in ways that challenge our greatest minds. And it's ours to explore, not with rockets and spaceships alone, though those will come, but with telescopes and mathematics, with curiosity and determination, with the uniquely human capacity to ask why and how, and refuse to accept silence as an answer. The cosmos is waiting. It's been waiting for billions of years, spinning out its story in starlight and chemistry, in the formation of galaxies and the birth of stars and the assembly of planets and the emergence of life. And now, finally, one species on one small world has developed the capability to read that story, to understand the cosmic narrative, to see ourselves as part of the grand tapestry. We are cosmic beings. We are made of elements forged in dying stars. We are built from the same matter that makes up everything in the universe, temporarily organized into patterns that can think and feel and wonder and discover. We are the universe's way of knowing itself, and that capacity, that consciousness, is perhaps the most precious thing that exists. Thank you for joining us on this journey through space and time, through science and speculation, through the detailed chemistry of distant atmospheres and the profound philosophical questions of existence and meaning. Thank you for caring about the cosmos, for wondering about distant worlds, for allowing yourself to feel the awe that comes from contemplating our place in the universe. Keep looking up. Keep asking questions. Keep seeking answers. Keep that sense of wonder alive, because wonder is where all discovery begins. It's the spark that ignites curiosity, the fuel that drives exploration, the foundation on which all scientific progress is built. Somewhere out there beneath alien skies and around a distant sun, life might be doing the same thing, looking up at its stars, wondering if it's alone, building instruments to search for signs of life on distant worlds, detecting our planet perhaps, seeing it as it was 120 years ago, analyzing our atmosphere, noting the oxygen and methane, and wondering if those biosignatures indicate the presence of life. Maybe, just maybe, they've found us the same way we've found them. Maybe they're having this same conversation on their world, contemplating the discovery of life on a planet 120 light years away, a world they call by some alien name, but we call Earth. And maybe someday we'll find a way to communicate, to bridge the vast gulf of space and time that separates us, to share knowledge, to compare notes on the universe, to learn from each other's unique perspectives and experiences. That day might be centuries away. It might be millennia. It might never come, but the possibility exists now in a way it never has before. We know we're not alone. We have evidence. We have data. We have reason to believe that life, real biological life, exists beyond Earth. And that changes everything. The universe is not empty. The stars are not mere decorations in the night sky. They are suns. They host worlds. Some of those worlds harbor life. And we, improbable as it seems, have developed the capability to detect that life across distances so vast they defy comprehension. That's not just science. That's miracle. Not in the supernatural sense, but in the sense that it's wonderful, amazing, awe-inspiring. We've reached across the void between stars and touched another living world, if only with instruments and mathematics and careful observation. The search continues. The discoveries will multiply. Our understanding will deepen. And through it all, that fundamental question that has haunted humanity since we first looked up at the night sky will gradually, patiently, persistently be answered. Are we alone? No, we are not alone. The universe is alive. And we're part of that vast living cosmos, connected to every other biosphere by the fundamental physics and chemistry that governs all things, by our shared origin in the Big Bang, by our common inheritance of star stuff forged in dying suns. Welcome to the cosmic community. Welcome to the universe as it really is. Vast, ancient, complex, beautiful, and wonderfully, gloriously alive with possibility. Thank you for joining Infinite Science on this extraordinary journey. Thank you for your curiosity, your attention, your willingness to contemplate questions that span from the molecular to the cosmic. Until next time, stay curious. Keep exploring. Keep wondering. Keep looking up at the stars and asking questions, because the greatest discoveries are still ahead. The most profound revelations are yet to come. And you, right now, in this moment, are part of the generation that will witness them. The universe is waiting. Go explore it.